The human body is always in motion, even when it appears to be still. Beneath the quiet rise and fall of the chest, beneath the steady beat of the heart, countless processes unfold with exquisite precision. Muscles contract, cells absorb nutrients, the brain hums with electrical impulses, and blood travels tirelessly through a network of vessels. But among all of these constant activities, there exists a subtler form of communication, one that does not rely on wires of nerves or quick sparks of electricity. Instead, it relies on messages carried in the bloodstream, chemical notes that drift slowly, yet purposefully from one organ to another. These messages are called hormones, and together they form a language of chemistry that shapes who we are, how we grow, how we feel, and how we adapt to the world around us. Hormones are unlike words or sounds. They cannot be heard, they cannot be seen, and yet their influence extends into nearly every aspect of human life. When a child grows taller, when an adult feels hunger or fullness, when a person falls asleep, or when the heart races in response to stress, it is hormones that help direct these changes. The system that produces and coordinates them is called the endocrine system, a collection of glands spread throughout the body, each releasing its own unique chemical messengers. Though small in size and often overlooked, these glands exert a quiet power, ensuring that the body remains in balance. The very word endocrine comes from Greek roots, endo, meaning within, and crine, meaning to secrete. Unlike other glands, which may release their products through ducts into the surface of the body, endocrine glands release their hormones directly into the bloodstream. Once released, these hormones travel through the circulatory system, mingling with blood cells and nutrients, until they reach distant tissues that are sensitive to their presence. These target tissues recognize the hormone through specific receptors, much like a lock opening only for the right key. Once unlocked, the cell responds, perhaps by speeding up its activity, by slowing it down, or by producing another substance in turn. This form of communication is slower than nerve impulses, but it is also more enduring. Whereas a nerve signal might cause a muscle to twitch in an instant, a hormone might alter metabolism for hours or even days. In this way, the nervous system and the endocrine system complement one another. The nervous system is quick, sharp, and localized. The endocrine system is slower, softer, but far-reaching. Together, they weave a network of control that allows the body to respond to immediate demands while also guiding long-term processes such as growth, reproduction, and aging. To imagine the role of hormones, it helps to think of them as part of a great orchestra. Each gland is like an instrument. The pituitary gland, often called the master gland, sits beneath the brain and conducts much of the ensemble, directing other glands when to play louder and when to soften. The thyroid gland sets the tempo of metabolism, speeding or slowing the body's use of energy. The adrenal glands contribute sudden crescendos in moments of stress. The pancreas ensures that the supply of glucose is balanced, neither too low nor too high, providing steady energy for all of life's activities. The ovaries and testes guide the rhythms of reproduction, while the pineal gland helps set the cycles of sleep and wakefulness. Each hormone is like a note, small in itself, yet meaningful when placed in the context of the whole. When we first begin to think of hormones, it may be tempting to reduce them to single functions. Insulin lowers blood sugar, melatonin induces sleep, estrogen supports fertility. Yet in truth, no hormone acts alone, and few have only one effect. A single hormone often influences many tissues, and a single process is often regulated by several hormones working together. This cooperation ensures stability, preventing any one gland from acting without oversight. A concept called feedback helps explain this. In negative feedback loops, The body measures the effects of a hormone and adjusts production accordingly. If blood sugar rises, insulin is released. As blood sugar falls again, insulin release diminishes. This gentle push and pull keeps the body from drifting too far in any one direction. The influence of hormones begins before birth and continues until the final days of life. During development in the womb, maternal and fetal hormones coordinate the growth of tissues and organs. At birth, a surge of adrenaline and other hormones prepares the infant to take its first breath. In childhood, growth hormone allows bones to lengthen and muscles to strengthen. In adolescence, sex hormones sculpt the body into its adult form, giving rise to the features that distinguish male from female. Throughout adulthood, hormones oversee digestion, energy, reproduction, and mood. Even in old age, when levels of many hormones decline, they continue to shape the body's adaptations to aging. Hormones not only regulate the physical state of the body, but also touch the inner landscape of emotion. The warmth of oxytocin during a hug, the surge of adrenaline during excitement, the calming influence of serotonin and melatonin as night approaches. These chemical messengers move between body and mind, showing that the distinction between the two is never absolute. Hormones reveal that emotions are not only experiences of the brain, but are also felt through the rhythms of the body. It is easy to overlook this hidden world because it works quietly. Unlike the pounding of the heart or the sharp intake of breath, hormone activity is subtle, gradual, and often invisible. Yet when hormones falter, their importance becomes suddenly clear. A deficiency of insulin leads to diabetes. Too little thyroid hormone slows metabolism, and too much cortisol may weaken the body over time. These conditions remind us of the delicate balance that must be maintained. But for most of us, most of the time, this balance holds steady without conscious thought, evidence of the body's remarkable design. As we begin this exploration of the endocrine system, we are invited to imagine the body not as a machine of parts working in isolation, but as a living symphony where every note matters. Hormones drift like invisible currents, linking organ to organ, guiding life with patience and precision. They are reminders that the body is more than physical structure. It is also a flow of signals, a quiet conversation carried out in molecules. To listen to this conversation is to understand a deeper rhythm, one that hums through every heartbeat, every breath, every night of sleep, and every day of waking life. This is the gentle world of hormones, a world without noise or haste, yet filled with direction and intention. As we move forward, we will step deeper into this world, visiting each gland and each messenger in turn, to see how together they sustain the story of life. 2. Hormones as chemical signals. When we think of communication within the body, the first image that often comes to mind is the nervous system. Nerves flash with electrical impulses, traveling from fingertip to brain in the blink of an eye, making us aware of heat, touch, or pain. But alongside this quicksilver network exists another, quieter system of communication, one that does not hurry, but instead moves at the pace of flowing blood. This is the endocrine system, and its messengers, the hormones, represent a language of chemistry. Unlike the nervous system, which speaks in bursts of electricity, hormones speak in molecules. They are dissolved into the bloodstream, carried with red and white blood cells, floating gently until they find the cells that are ready to listen. The fundamental difference between these two ways of signaling is speed and duration. Nervous impulses are swift and fleeting. A muscle contracts, a finger withdraws, a thought forms. Hormones, by contrast, may take seconds, minutes, or even hours to exert their effects, and once released, their influence lingers. The quick flash of adrenaline prepares a person to respond immediately to stress. But cortisol, another hormone released in tandem, may shape the body's response for hours afterward. Insulin, once secreted into the blood, continues to regulate the entry of glucose into cells for much of the day. In this way, hormones are not simply messengers of urgency but guides of ongoing activity, steadying the rhythms of life. Each hormone is a molecule with a particular structure, and that structure determines its target. Some hormones are proteins, strings of amino acids folded into unique shapes. Others are steroids, derived from cholesterol, able to slip easily across the oily barrier of cell membranes. A few, such as melatonin, are simple derivatives of amino acids, small and nimble molecules that act as signals of time and light. What unites them all is their ability to find and bind to receptors. A receptor is a specialized protein, embedded in the surface of a cell or hidden within its interior, waiting for the precise hormone that will fit like a key into its lock. Once that connection is made, the receptor changes shape, sending a cascade of signals inside the cell. This may alter the cell's metabolism, its growth, its production of proteins, or even the way it communicates with other cells. It is important to note that hormones do not act indiscriminately. Though they travel everywhere the blood flows, only cells with the right receptors will respond. This is why the same hormone can circulate throughout the body, yet produce specific effects in only a handful of tissues. For instance, insulin is present in every capillary of the body, yet only muscle, liver, and fat cells respond by absorbing glucose. Thyroid hormone drifts in the bloodstream continuously, but only cells with thyroid receptors alter their metabolic pace in response. This selectivity ensures that hormones remain precise, guiding the body without creating chaos. There are also differences in how hormones deliver their messages depending on their chemical nature. Steroid hormones, such as cortisol or estrogen, dissolve into the fatty layers of cell membranes and slip through to the inside of the cell. Once inside, they often bind to receptors within the nucleus, directly influencing the expression of genes. They can turn genes on or off, leading to long-lasting changes in the proteins a cell produces. Protein-based hormones, like insulin or growth hormone, cannot cross the fatty barrier so easily. Instead, they bind to receptors on the surface of the cell. This binding triggers a chain reaction of signals within the cell, using molecules such as cyclic AMP or calcium as second messengers. These cascades amplify the signal, allowing even a tiny concentration of hormone to produce a significant effect. The timing of hormone release is also carefully controlled. Some hormones are secreted in steady amounts, maintaining a constant background level. Thyroid hormones are a good example, released gradually to set the body's general metabolic tone. Others are secreted in pulses, surging and ebbing according to need. Insulin rises after meals and falls during fasting. Cortisol follows a daily rhythm, peaking in the morning to prepare the body for waking and diminishing at night to allow rest. Still others are secreted in response to special circumstances. Adrenaline is released during moments of stress or excitement, oxytocin during childbirth and nursing, and melatonin during darkness to promote sleep. The body does not waste these signals. It delivers them in patterns tuned to the rhythms of life. A key feature of endocrine signaling is feedback regulation. This ensures that hormones do not spiral out of control. Negative feedback is the most common mechanism. When a hormone's effect reaches a certain level, it sends signals back to the gland to reduce production. For example, when thyroid hormones increase in the blood, they signal the pituitary gland to release less thyroid-stimulating hormone. This loop keeps levels steady, preventing extremes. Positive feedback is rarer but powerful. During childbirth, the hormone oxytocin stimulates uterine contractions, which in turn cause more oxytocin to be released, creating a cycle that intensifies until birth occurs. These feedback systems are nature's way of keeping the conversation balanced, neither too loud nor too quiet. Hormones also communicate in different ranges. The classic endocrine signal travels through the blood to distant tissues, but there are variations. In paracrine signaling, hormones act locally, influencing neighboring cells without entering the bloodstream. In autocrine signaling, a cell releases a hormone that acts on itself, a way of fine-tuning its own activity. These subtle layers of communication reveal that hormones are not only global messengers but also local regulators, able to shape activity on every scale. The elegance of this chemical communication becomes even clearer when we consider how multiple hormones interact. Rarely does one hormone act alone. The regulation of blood sugar, for instance, depends on the balance between insulin, which lowers glucose, and glucagon, which raises it. The stress response involves adrenaline for speed, cortisol for endurance, and aldosterone to maintain salt and water balance. Even reproduction relies on the interplay of estrogen, progesterone, luteinizing hormone, and follicle-stimulating hormone. Each hormone contributes its own voice, but together they form chords and harmonies, ensuring that the body responds not in fragments but as a unified whole. This quiet conversation through chemistry extends beyond the human body into the wider world of biology. Plants, too, have hormones that regulate growth, flowering, and adaptation to the seasons. In animals, hormones often serve as signals between individuals, as in the case of pheromones that influence mating behavior. The endocrine language, then, is not unique to humans but is a universal strategy of life, a way for living systems to maintain order and adapt to change. In essence, hormones embody the idea that the body is not simply a collection of organs working in isolation. Instead, it is a community bound together by shared messages, drifting molecules that tie the brain to the bones, the stomach to the muscles, the glands to the emotions. To understand hormones is to glimpse the hidden dialogue that never stops, a dialogue that underlies hunger and rest, growth and maturity, love and stress, energy and calm. It is not a dialogue of words, but of molecules, patient and precise, shaping life from within. As we continue, we will turn our attention to the first of the great conductors of this system, the hypothalamus and pituitary gland, to see how they orchestrate much of this chemistry, ensuring that the symphony of hormones remains in harmony. 3. The hypothalamus, bridge of control. Deep within the brain, nestled beneath the thalamus and above the pituitary gland, lies a structure no larger than the tip of a thumb. Despite its modest size, the hypothalamus exerts a profound influence over the body, serving as one of the most important bridges between the nervous system and the endocrine system. To appreciate its role, one must imagine the brain as both a command center and a translator. The brain senses the world around us: light, sound, temperature, danger, comfort, and then must decide how the body should respond. But the language of the brain is electrical, traveling through nerves, while the language of the body's organs is often chemical, communicated through hormones. The hypothalamus, sitting quietly at this crossroads, is the translator that converts thought into chemistry, experience into molecular signals, and perception into physiology. The hypothalamus has many tasks, but at its heart lies the regulation of homeostasis, the delicate balance of internal conditions that allows the body to survive and thrive. It constantly monitors cues from the body: the temperature of the blood, the concentration of nutrients, the presence of hormones, and even emotional states. If the body grows too warm, the hypothalamus activates mechanisms to release heat. If the body is dehydrated, it sends signals that generate thirst. If energy stores are low, it adjusts hunger and metabolism to encourage the intake of food. In this way, the hypothalamus does not rest. It is always surveying, always adjusting, always seeking equilibrium. One of the most significant roles of the hypothalamus is its control over the pituitary gland, the small yet mighty organ, often called the master gland. The pituitary hangs just below the hypothalamus, connected by a slender stalk known as the infundibulum. Through this connection, the hypothalamus delivers hormones and nerve signals that dictate the pituitary's activity. The hypothalamus itself produces special hormones called releasing hormones and inhibiting hormones. These chemicals are secreted into a small system of blood vessels that directly connect to the pituitary, ensuring swift and precise communication. For instance, thyrotropin-releasing hormone from the hypothalamus prompts the pituitary to release thyroid-stimulating hormone, which then acts on the thyroid gland to regulate metabolism. Corticotropin-releasing hormone, similarly, triggers the pituitary to release adrenocorticotropic hormone, which influences the adrenal glands and shapes the body's response to stress. In this way, the hypothalamus sits at the top of a cascade of control, where a signal from the brain can ripple downward through glands, eventually altering the activity of cells throughout the body. But the hypothalamus is not only a controller of glands, it is also directly a gland in its own right. It produces hormones such as oxytocin and vasopressin, which are transported down nerve fibers into the posterior pituitary, where they are stored and eventually released into the bloodstream. Oxytocin plays roles in childbirth, nursing, and social bonding, creating feelings of closeness and trust. Vasopressin, also known as antidiuretic hormone, helps the body conserve water by acting on the kidneys. These hormones remind us that the hypothalamus does not simply observe and direct. It actively participates in the chemical communication that sustains life. Another important aspect of hypothalamic function lies in its control of circadian rhythms, the internal clock that governs cycles of sleep and wakefulness. Within the hypothalamus sits the suprachiasmatic nucleus, a cluster of neurons that responds to light cues received through the eyes. This tiny cluster helps synchronize the body's rhythms with the cycle of day and night. When light fades, it signals the pineal gland to release melatonin, preparing the body for rest. When morning light returns, the signal shifts, melatonin declines, and the body awakens. This daily rhythm is not only about sleep, but also about metabolism, hormone release, and even mood, all subtly tuned to the passage of time by the hypothalamus. The hypothalamus also interacts with the limbic system, the brain's emotional center. Emotions such as fear, joy, and anger do not remain confined to thought. They echo through the body as physical sensations. The racing heart in fear, the warmth of affection, the trembling in anger, all are shaped by the hypothalamus, which translates emotional states into hormonal and physiological responses. This connection ensures that the mind and body are not separate entities, but a continuous whole. When the brain perceives danger, the hypothalamus is among the first to react, stimulating the release of stress hormones that prepare the body for action. When the brain experiences comfort and safety, the hypothalamus fosters relaxation, digestion, and restorative processes. The influence of the hypothalamus extends into growth, reproduction, and metabolism, often in subtle ways that unfold over long periods. In childhood, its releasing hormones guide the pituitary to secrete growth hormone, shaping bones and muscles as the body develops. In adolescence, the hypothalamus triggers the pituitary to release hormones that activate the gonads, leading to the cascade of changes known as puberty. In adulthood, it continues to monitor energy intake and expenditure, adjusting appetite and metabolism according to the body's needs. Even in aging, the hypothalamus remains active, though its signals may shift, contributing to the natural changes in sleep patterns, energy, and hormonal balance that accompany later life. One of the striking qualities of the hypothalamus is its dual nature as both a nervous and endocrine structure. It contains neurons that transmit electrical impulses, yet it also produces hormones that drift through the blood. This dual role exemplifies the unity of the nervous and endocrine systems. Rather than two separate systems, They are intertwined, and the hypothalamus is the clearest demonstration of this unity. It is both brain and gland, thought and chemistry, a living bridge that ensures the two languages of the body are always in conversation. The precision of hypothalamic control can be appreciated through examples of what happens when it falters. Damage or dysfunction of the hypothalamus may disrupt thirst, hunger, temperature regulation, or sleep. In some cases, hormone release from the pituitary is altered, leading to conditions such as hypothyroidism or adrenal insufficiency. These conditions remind us that the hypothalamus, though small, holds the reins of balance, and without its careful oversight, the harmony of the endocrine orchestra begins to waver. Yet for most of us, this structure performs its duties silently and faithfully, adjusting every moment without notice, a quiet guardian of stability. As one reflects on the hypothalamus, it becomes clear that its power lies not in strength or size, but in coordination. It listens to the brain, it listens to the body, and it ensures that both are heard in equal measure. It translates hunger into action, fear into readiness, fatigue into sleep, and growth into possibility. It does so without pause, without fatigue, through day and night, through the stages of life. To know the hypothalamus is to understand that the body is always conversing with itself, that the nervous system and the endocrine system are not separate realms, but threads, woven together into one fabric of life. The story of hormones would not be complete without this bridge, for it is the hypothalamus that links thought to physiology, mind to body, the fleeting perception of a moment to the lasting chemistry of change. As we continue to explore the endocrine system, we will carry with us the image of this small but vital structure, resting in the center of the brain, guiding the orchestra of hormones with precision, ensuring that every signal finds its way into the great harmony of life. 4. The pituitary gland, master conductor, suspended from the base of the brain like a small pearl on a delicate stalk. The pituitary gland is often described as the master gland of the endocrine system. Its size is modest, no larger than a pea, yet its influence extends across nearly every system of the body. It is sheltered within a bony hollow at the base of the skull, the sella turcica, as though nature understood its importance and offered it special protection. From this quiet position, the pituitary releases a suite of hormones that orchestrate growth, reproduction, metabolism, and adaptation. To imagine the body as an orchestra is to understand the pituitary as its conductor, lifting its hand to cue one section, quiet another, and bring the entire ensemble into balance. The pituitary does not work alone. Above it lies the hypothalamus, a master in its own right, sending instructions through releasing and inhibiting hormones that guide the pituitary's output. The relationship between the two is intimate. A stalk of tissue called the infundibulum links them, carrying both nerves and tiny blood vessels. Through this connection, the hypothalamus whispers its commands, and the pituitary responds with hormones that reach far beyond the brain. This partnership ensures that the pituitary is both brain-driven and body-focused, acting as the crucial middle point between thought and physiology. The pituitary gland is divided into two distinct parts, the anterior lobe and the posterior lobe. Though they are fused into a single organ, their functions and methods of control are quite different. The anterior lobe, also called the adenohypophysis, is where most of the classical pituitary hormones are produced. These hormones include growth hormone, prolactin, thyroid-stimulating hormone, adrenocorticotropic hormone, and the gonadotropins luteinizing hormone and follicle-stimulating hormone. Each of these has far-reaching effects, touching tissues throughout the body. The posterior lobe, or neurohypophysis, does not produce hormones itself, but instead stores and releases oxytocin and vasopressin, both crafted in the hypothalamus and delivered through nerve fibers. Together, The two lobes embody the dual nature of the pituitary. One, a gland of production, the other, a gateway of release. Growth hormone, as its name suggests, plays a central role in the development of the body. During childhood and adolescence, it stimulates the growth of bones and muscles, ensuring that the skeleton lengthens and the body gains strength. But growth hormone does not disappear with adulthood. It continues to influence metabolism, encouraging protein synthesis, supporting the repair of tissues, and mobilizing fat for energy. Its effect is subtle yet constant, allowing the body to renew itself day by day. Without adequate growth hormone, growth falters in the young, and in adults, the balance of body composition and energy shifts unfavorably. With too much, growth becomes excessive, leading to conditions such as gigantism or acromegaly, reminders of the precision required in hormonal balance. Prolactin is another product of the anterior pituitary, notable for its role in stimulating milk production after childbirth, but its functions extend beyond nursing. Prolactin influences reproductive behavior, immune regulation, and even emotional bonding between parent and child. In many mammals, prolactin is associated with nurturing behaviors, a reminder that hormones not only shape physical states, but also contribute to the subtler qualities of life, such as care and attachment. Thyroid-stimulating hormone, often abbreviated as TSH, is the pituitary's signal to the thyroid gland. When released into the bloodstream, it travels to the thyroid in the neck and prompts the release of thyroid hormones. These hormones, in turn, regulate the pace of metabolism, setting the speed at which the body uses energy. The pituitary does not generate metabolism directly, but through TSH it holds the dial that adjusts the body's energetic tempo. This feedback loop ensures that the thyroid does not act in isolation but as part of the larger harmony of endocrine control. Adrenocorticotropic hormone, or ACTH, directs the adrenal cortex, the outer layer of the adrenal glands perched above the kidneys. ACTH stimulates the release of cortisol, a hormone vital for managing stress, regulating blood sugar, and influencing immune function. Through ACTH, the pituitary links the perception of stress in the brain to the body's chemical response, ensuring that challenges are met with the proper mobilization of resources. In this way, a thought of danger or a moment of strain can trigger a cascade that flows from brain to pituitary to adrenal gland, and finally, into every cell of the body. The pituitary also produces gonadotropins, luteinizing hormone, and follicle-stimulating hormone, which regulate the ovaries and testes. These hormones guide reproductive cycles, fertility, and the production of sex hormones such as estrogen, progesterone, and testosterone. They orchestrate the changes of puberty, the monthly rhythms of the menstrual cycle, and the continual production of sperm. Through them, the pituitary shapes the possibilities of reproduction and the continuation of life itself. The posterior pituitary plays a quieter but equally profound role. Here, oxytocin and vasopressin are released into the bloodstream. Oxytocin is well known for its role in childbirth, where it stimulates contractions, and in lactation, where it aids the release of milk, yet it is also called the bonding hormone, involved in social attachment, trust, and emotional closeness. Vasopressin, or antidiuretic hormone, acts on the kidneys to conserve water, preventing dehydration and helping maintain blood pressure. These two hormones remind us that survival is not only about individual physiology, but also about connection, reproduction, and cooperation, all threads in the fabric of human life. The influence of the pituitary is strikingly broad. From the moment of birth, it is active. In infancy, it supports growth. In adolescence, it awakens reproductive capacity. In adulthood, it maintains energy balance, fertility, and stress adaptation. In later life, its changing rhythms contribute to the shifts of aging. Few organs touch so many stages of existence, yet the pituitary accomplishes this with only a handful of hormones, each carrying messages that ripple outward. It is worth noting that the pituitary does not act in isolation, nor does it simply command without listening. Feedback loops are central to its function. The hormones it stimulates often send signals back to suppress further release, creating a balanced cycle. For instance, when thyroid hormones rise, they feed back to both pituitary and hypothalamus to reduce TSH production. When cortisol levels climb, they signal back to quiet the release of ACTH. This self-regulation prevents extremes and maintains stability, an elegant demonstration of the body's preference for equilibrium. When the pituitary falters, the effects are profound because its reach is so wide. A deficiency in pituitary hormones can lead to stunted growth, infertility, fatigue, and imbalance across multiple systems. An excess can lead to overgrowth, overstimulation of glands, and metabolic strain. Disorders of the pituitary remind us how interconnected the body is, for when this tiny gland suffers, the ripples are felt in bones, muscles, organs, and emotions alike. Yet when it functions normally, it does so in silence, its influence woven so seamlessly into life that we rarely notice it. The image of the pituitary as master conductor is apt, for it listens as well as directs, responding to cues from the hypothalamus above and to feedback from the glands below. It stands at the center of a network, balancing command with cooperation, ensuring that no section of the body's orchestra plays too loudly or too softly. In its quiet way, it unites the body's many voices into a single harmony, sustaining life, moment by moment, from childhood through old age. To reflect on the pituitary is to recognize how something so small can hold such vast importance, a reminder that in the body, as in life, power is not always measured by size, but by connection. 5. The thyroid gland, keeper of energy, at the base of the neck, just below the larynx, and wrapped gently around the trachea, rests a butterfly-shaped gland whose influence touches every cell in the body. The thyroid gland, though small and easily overlooked, is one of the most important regulators of human life. Its role is to maintain the pace at which the body uses energy, shaping metabolism, temperature, and growth. Like the tempo of a song, thyroid hormones set the rhythm for countless processes, ensuring that life proceeds neither too slowly nor too quickly, but at a steady pace suited to survival and well-being. To imagine life without the thyroid's influence is to imagine a world where the music of physiology falters, sometimes sluggish and heavy, sometimes frantic and unstable. The thyroid produces two principal hormones, thyroxine, often abbreviated as T4, and triiodothyronine, or T3. Though their names sound complex, their function is straightforward. They regulate how fast cells convert nutrients into usable energy. T4, containing 4 iodine atoms, is the more abundant hormone, but it is T3, with 3 iodine atoms, that is more active and potent. Much of the T4 released by the thyroid is later converted into T3 in tissues throughout the body, a reminder that hormones often work in partnership, passing signals forward in a chain of transformation. Both T3 and T4 are carried through the bloodstream, bound to proteins that allow them to circulate, and they slip into cells to influence metabolism directly. The production of thyroid hormones is guided by the pituitary gland, which releases thyroid-stimulating hormone, or TSH. This in turn is controlled by thyrotropin-releasing hormone from the hypothalamus. Together, these three structures form a chain of command known as the hypothalamic-pituitary-thyroid axis. When thyroid hormones in the blood fall too low, the hypothalamus prompts the pituitary, which in turn signals the thyroid to increase output. As levels rise, they feed back to quiet the system, ensuring that hormone concentrations remain within a healthy range. This elegant loop, like a thermostat, maintains balance and prevents extremes. The influence of thyroid hormones is vast. At the cellular level, they increase the production of enzymes and proteins that drive metabolism. They stimulate the mitochondria, the powerhouses of the cell, to produce more energy in the form of ATP. They enhance the breakdown of carbohydrates and fats, releasing fuel for the body. They also influence the synthesis of proteins, supporting growth and repair. Because nearly every cell in the body depends on energy, nearly every cell is touched by thyroid hormones. From the beating of the heart to the contraction of muscles, from the firing of neurons to the renewal of skin, the thyroid quietly ensures that energy is available and properly used. Beyond cellular metabolism, thyroid hormones shape whole body functions. They increase the rate of the heartbeat and the force of cardiac contractions, ensuring that blood delivers oxygen and nutrients efficiently. They influence breathing, encouraging the lungs to take in oxygen and release carbon dioxide. They generate heat, helping the body maintain temperature in the face of a changing environment. They also play a role in digestion, muscle strength, and even mood, showing that their effects extend into both the physical and emotional dimensions of life. During development, the thyroid's influence is even more critical. In infants and children, thyroid hormones guide the growth of the skeleton, the maturation of the brain, and the development of the nervous system. A deficiency during early life can lead to delayed growth and impaired intellectual development, a condition historically known as cretinism. This underscores the essential role of iodine, the mineral required to build thyroid hormones. Without sufficient iodine in the diet, the thyroid cannot produce T3 and T4 effectively, and the consequences ripple outward into every aspect of growth. For this reason, iodine has been added to table salt in many parts of the world, a simple measure that prevents widespread deficiency and protects the health of future generations. The thyroid gland is also home to another set of cells that secrete calcitonin, a hormone involved in calcium regulation. Though its role is less pronounced than that of parathyroid hormone, calcitonin helps reduce blood calcium levels by promoting the deposition of calcium into bones. In this way, the thyroid participates not only in energy metabolism, but also in maintaining the balance of minerals, subtly contributing to the strength and structure of the skeleton. Disorders of the thyroid illustrate its power by showing what happens when its balance is lost. When the gland becomes underactive, a condition known as hypothyroidism, the body slows, metabolism decreases, leading to fatigue, weight gain, cold intolerance, dry skin, and sluggish thought. Even the heartbeat becomes slower and weaker. In contrast, when the gland becomes overactive, a condition called hyperthyroidism, the body accelerates. Metabolism speeds up, producing weight loss despite increased appetite, restlessness, heat intolerance, rapid heartbeat, and tremors. The eyes may appear prominent, and the skin may feel warm and moist. Both conditions reveal that the thyroid is not optional, but essential, a guardian of balance, whose absence or excess destabilizes the entire body. The thyroid is also susceptible to structural changes, such as goiters, which are enlargements of the gland. Goiters may result from iodine deficiency or from autoimmune conditions such as Graves' disease or Hashimoto's thyroiditis. These conditions highlight the complex interplay between the immune system and the endocrine system. For sometimes the body's defenses mistakenly attack its own thyroid cells, leading to dysfunction. Yet even in these disorders, the underlying truth remains. The thyroid's role is so central that when it falters, the effects are felt everywhere. Despite these vulnerabilities, the thyroid is remarkably resilient. It can adapt to changes in dietary iodine, adjust its output to the body's needs, and recover from temporary imbalances. Its small size belies its capacity, for within its two lobes lies a factory of hormones that quietly sustain life. Each follicle of the thyroid is filled with a substance called colloid, rich in thyroglobulin, the precursor of T3 and T4. When stimulated by TSH, these follicles spring into action, assembling hormones atom by atom, a microscopic workshop whose products ripple outward into the grand theater of physiology. It is humbling to consider how a small gland in the neck can influence thought, mood, temperature, growth, and vitality. Yet this is the nature of the endocrine system. Small structures, invisible and silent, wield immense influence. The thyroid teaches us that energy is not simply about calories eaten or muscles moved, but about the pace of life itself, determined by molecules that drift silently in the blood. It is the keeper of energy, the guardian of tempo, ensuring that life does not fall into stillness or spin into chaos, but instead moves forward with steady rhythm. As we continue our journey through the endocrine system, the thyroid stands as a symbol of balance and rhythm. Its butterfly shape may remind us of lightness and transformation, and indeed it is a gland that allows transformation at every stage of life, from growth in childhood to vitality in adulthood and to adaptation in age. To understand the thyroid is to recognize that energy itself is not random but carefully measured, released in just the right amount to sustain life's quiet song. 6. The parathyroids, guardians of calcium. Nestled quietly behind the thyroid gland are 4 tiny structures. So small they are often overlooked even by those studying anatomy for the first time. These are the parathyroid glands. And though they weigh less than a grain of rice, their role in the body is immense. They act as vigilant guardians of calcium, one of the most important minerals in human physiology. Without calcium, muscles could not contract, nerves could not transmit signals, and blood could not clot. The very heartbeat itself depends on calcium flowing in and out of cells in precise patterns. It is the parathyroid glands that keep this mineral balanced, never too high and never too low, adjusting moment by moment with extraordinary sensitivity. Calcium is stored primarily in the skeleton, which holds a vast reserve of this mineral locked within bone. Yet bones are not static. They are dynamic tissues constantly being broken down and rebuilt. The parathyroid glands monitor the level of calcium in the blood and direct this flow between bone and bloodstream. When calcium levels drop too low, they respond by releasing parathyroid hormone, often abbreviated as PTH. This hormone signals bones to release calcium, kidneys to conserve it, and intestines to absorb more of it. When calcium levels rise again, PTH secretion diminishes, allowing balance to return. Through this continuous cycle, the parathyroids ensure that calcium remains within a narrow range, preserving stability for the entire body. Parathyroid hormone works through several pathways at once. In bone, it stimulates specialized cells called osteoclasts to break down bone tissue, releasing calcium into the blood. This might seem destructive at first glance, but it is essential for maintaining the supply of calcium when dietary intake is insufficient. Meanwhile, in the kidneys, PTH reduces calcium excretion, conserving what would otherwise be lost in urine. It also stimulates the kidneys to activate vitamin D, converting it into its usable form, calcitriol. This activated vitamin D then travels to the intestines, where it increases the absorption of calcium from food. The result is a coordinated effort across bone, kidney, and gut, all directed by the parathyroids to restore calcium balance. The importance of this regulation cannot be overstated. Calcium is required not only for strong bones, but also for the basic function of cells. In muscle, calcium triggers contraction, allowing every movement from the blink of an eye to the steady rhythm of breathing. In neurons, calcium enables the release of neurotransmitters, the chemicals that allow signals to pass from one cell to another. In the blood, calcium is essential for clotting, preventing excessive bleeding from even the smallest injury. The body therefore guards its calcium levels with extraordinary care, and it is the parathyroids that act as watchful sentinels, ensuring that this mineral is always available in just the right amount. When the parathyroid glands falter, the consequences are immediate and severe. If PTH is deficient, as in hypoparathyroidism, calcium levels in the blood drop dangerously low, a condition known as hypocalcemia. This leads to muscle cramps, tingling sensations, spasms, and in severe cases, life-threatening seizures or irregular heartbeats. The body becomes overly excitable, as nerves fire unpredictably without enough calcium to stabilize their activity. On the other hand, if the parathyroid glands produce too much PTH, as in hyperparathyroidism, calcium levels rise excessively, leading to hypercalcemia. This condition weakens bones as they release too much calcium, increases the risk of kidney stones as calcium accumulates in the urine, and disrupts the function of muscles and nerves. Both extremes reveal the necessity of parathyroid balance, for too little or too much calcium destabilizes the entire body. Despite their size, the parathyroid glands are remarkably sophisticated in their sensitivity. They contain calcium-sensing receptors on their surface that continuously monitor the concentration of calcium in the blood. These receptors are so precise that they can detect even the smallest fluctuations and adjust PTH release accordingly. This continuous monitoring and response occur without conscious effort, another reminder of how much of life's regulation happens beneath awareness. While we go about daily activities, walking, eating, resting, the parathyroids are at work, silently adjusting calcium to keep every muscle fiber and nerve cell ready for action. The relationship between parathyroid hormone and vitamin D illustrates the cooperative nature of the endocrine system. Without PTH, the kidneys would not activate vitamin D efficiently, and without vitamin D, the intestines would not absorb calcium adequately. This partnership ensures that calcium taken in from the diet is effectively used. It also explains why vitamin D deficiency, common in areas with limited sunlight exposure, often leads to problems with calcium balance and bone health. Rickets in children and osteomalacia in adults are conditions that arise when bones become soft and weak due to poor mineralization, a direct consequence of inadequate vitamin D and disrupted parathyroid regulation. Bones themselves are deeply shaped by the actions of the parathyroids. Though often thought of as rigid structures, bones are dynamic, with cells constantly breaking down old tissue and building new. PTH influences this remodeling process, tipping the balance toward bone resorption when calcium is needed, and allowing rebuilding when levels are sufficient. Over time, this cycle of breakdown and repair strengthens bones, ensuring they remain adaptable to stress and strain. Without the guiding hand of the parathyroids, this cycle would lose direction, leading either to fragile bones starved of calcium or to brittle bones overloaded with it. The parathyroid glands also remind us of the interconnectedness of all organ systems. Their influence touches the skeletal system, the muscular system, the nervous system, the cardiovascular system, and even the digestive system. Few other glands exert such a wide range of effects through the regulation of a single mineral. It is a striking example of how life depends not only on complex organs but also on simple elements like calcium, sodium, and potassium, each carefully balanced to sustain the choreography of physiology. Though hidden behind the thyroid and often overshadowed by its more famous neighbor, the parathyroid glands deserve recognition for their constant, tireless work. They may be small, but they are guardians of one of life's most essential minerals, ensuring that every heartbeat, every thought, and every movement can occur smoothly. Their vigilance is unceasing, adjusting moment by moment as calcium flows through the blood, as bones release and store it, as kidneys filter it, and as intestines absorb it. They embody the principle that balance, rather than abundance, is the true key to health. To reflect on the parathyroids is to see the importance of subtlety in biology. Not every gland shouts with dramatic effects. Some whisper quietly, making small adjustments that sustain life's foundation. Calcium does not announce itself, but without it, life cannot proceed. The parathyroids ensure that this quiet mineral remains in harmony, a steady presence that allows the body to move, think, and heal. In their silence lies strength, and in their constancy lies survival. As we continue through the endocrine system, we move from these tiny guardians of calcium to other glands whose influence spreads across metabolism and energy. Yet the lesson of the parathyroids remains. Even the smallest parts of the body hold immense responsibility, and even the quietest signals can shape the entire rhythm of life. 7. The pancreas, regulator of glucose. Tucked behind the stomach and nestled in the curve of the duodenum lies an elongated organ that works in silence, performing two roles at once. The pancreas is both an exocrine and endocrine gland, serving digestion on one hand and hormonal regulation on the other. It is this second role, its function as an endocrine organ, that reveals the pancreas as the body's quiet regulator of glucose, ensuring that energy remains available to every cell in just the right amount. Unlike the heart, which beats with a rhythm we can feel, or the lungs, which fill with air we can sense, the pancreas carries out its duties without notice. Yet the balance it maintains is one upon which life itself depends. For glucose is the primary fuel of the body, and without its regulation, the machinery of life would falter. The pancreas contains clusters of specialized cells known as the islets of Langerhans, scattered like small islands within the larger sea of digestive tissue. These islets contain several types of hormone-producing cells, each with its own distinct role. The alpha cells secrete glucagon, a hormone that raises blood glucose levels. The beta cells produce insulin, the central hormone that lowers glucose levels by promoting its uptake into cells. Delta cells release somatostatin, which helps modulate the release of both insulin and glucagon. There are also other minor cell types contributing to the fine-tuned balance, but insulin and glucagon remain the principal actors in the story of glucose regulation. To understand the pancreas is to understand the delicate equilibrium between insulin and glucagon. When we eat, carbohydrates are broken down into glucose, which enters the bloodstream. Blood sugar rises, and the pancreas responds by releasing insulin from its beta cells. Insulin acts like a key, unlocking the doors of cells so that glucose can enter. Muscle and fat cells absorb glucose for use or storage, while the liver converts excess glucose into glycogen, a stored form of sugar that can be released later when needed. In this way, insulin prevents blood sugar from climbing too high after meals, protecting the body from the harmful effects of excess glucose. When blood sugar falls, as it does between meals or during fasting, the pancreas releases glucagon from its alpha cells. Glucagon prompts the liver to break down glycogen into glucose and release it back into the bloodstream. It also encourages the production of new glucose from amino acids and other substrates in a process known as gluconeogenesis. These actions raise blood sugar levels, preventing them from dropping too low. Thus, insulin and glucagon work as balancing forces, one lowering glucose when it rises, the other raising it when it falls. Together, they keep blood sugar within a narrow range, ensuring a steady supply of energy to the brain, muscles, and organs. The significance of this balance is immense, for glucose is the primary energy source for most of the body's cells and the essential fuel for the brain. Unlike muscles, which can burn fat for energy in times of scarcity, the brain depends almost entirely on glucose. Even slight deviations in blood sugar levels can impair thought, mood, and coordination. Severe deviations can be life-threatening. Hypoglycemia, or low blood sugar, can lead to confusion, seizures, and loss of consciousness. Hyperglycemia, or high blood sugar, can damage blood vessels, nerves, and organs if sustained over time. The pancreas prevents these extremes, maintaining stability so quietly that we rarely think of it at all. When the pancreas falters, however, the consequences are unmistakable. Diabetes mellitus is the most well-known disorder of pancreatic function. In type 1 diabetes, the immune system mistakenly destroys the beta cells of the pancreas, leaving the body unable to produce insulin. Without insulin, glucose cannot enter cells effectively, and blood sugar rises dangerously high. This condition requires lifelong insulin replacement for survival. In type 2 diabetes, the pancreas may still produce insulin, but the body's cells become resistant to its effects. Over time, insulin production may also decline. This leads again to elevated blood sugar, but through a different mechanism. Both forms of diabetes reveal the central role of insulin and the vulnerability of the balance it maintains. The pancreas also demonstrates the principle of feedback control that runs throughout the endocrine system. Rising glucose triggers insulin release, which in turn lowers glucose, quieting the stimulus. Falling glucose triggers glucagon, which raises it again. Each hormone is released in response to the very changes it corrects, creating loops of adjustment that keep the body steady. These loops operate with remarkable sensitivity, adjusting not only to meals but also to activity, stress. During exercise, for example, muscles demand more glucose, and the pancreas responds by modulating insulin and glucagon to ensure a steady supply of fuel. During sleep, when energy demands are lower, insulin secretion falls, allowing glucose to remain at appropriate levels without being depleted. The pancreas also interacts with other hormones to refine its regulation of energy. Cortisol from the adrenal glands, growth hormone from the pituitary, and epinephrine from the adrenal medulla all influence glucose levels, particularly during stress. These hormones ensure that energy is mobilized quickly when the body must respond to challenges. Yet the pancreas remains central, fine-tuning the response to keep glucose within safe limits. This interplay illustrates once more that no gland acts alone. Each is part of the wider conversation of the endocrine system. One of the most fascinating aspects of the pancreas is its ability to anticipate changes. When we begin to eat, even before glucose has entered the blood, the pancreas may start releasing insulin. This anticipatory response, called the cephalic phase, is triggered by signals from the nervous system when food is tasted or even smelled. It prepares the body for the incoming nutrients, smoothing the rise in blood sugar before it becomes significant. This demonstrates the close link between the nervous and endocrine systems, with the pancreas responding not only to chemical changes but also to sensory experiences. Despite its critical importance, the pancreas often goes unnoticed until something goes wrong. Its position deep in the abdomen makes it invisible to casual observation, and its hormones are silent, without sensation. Yet every meal, every period of fasting, every exertion depends on its continuous adjustments. It is the regulator of glucose, the guardian of energy, ensuring that the fuel of life is always available in just the right amount. Its work allows the body to move effortlessly from feast to fast, from rest to exertion, from waking to sleep. Reflecting on the pancreas invites us to consider how finely tuned the body truly island. The concentration of glucose in the blood is measured in milligrams per deciliter, yet the pancreas can sense minute changes and respond instantly. Its hormones circulate in tiny amounts, yet their impact is enormous. This is the hallmark of endocrine regulation. Small signals with far-reaching consequences, precise adjustments that sustain the rhythm of life. The pancreas embodies this principle fully, reminding us that balance is not achieved by force, but by quiet, constant attention. As we journey further into the endocrine system, we see how each gland contributes its own voice to the body's harmony. The pancreas, with its steady regulation of glucose, provides the foundation of energy upon which all other processes depend. Without it, the muscles could not move, the brain could not think, and the heart could not beat in rhythm. It is the unseen steward of energy, its quiet vigilance, allowing life to continue without interruption, meal by meal, day by day. 8. The adrenal glands, responding to stress. Resting like small caps on top of each kidney are a pair of triangular glands whose work extends far beyond their modest size. These are the adrenal glands, sometimes called suprarenal glands because of their position above the kidneys. Though each is only a few centimeters in length, together they are among the most powerful regulators of the body's responses to the world. They act swiftly in moments of danger and steadily in times of endurance, preparing the body to meet challenges, conserve resources, and recover from strain. The adrenal glands are guardians of survival, producing hormones that help the body respond to stress in its many forms: physical exertion, emotional tension, illness, or even the simple fluctuations of daily life. Each adrenal gland has two distinct regions, the outer cortex and the inner medulla, and each of these layers performs different tasks. The adrenal cortex produces steroid hormones, while the adrenal medulla releases catecholamines, such as adrenaline and noradrenaline. This division allows the adrenal glands to act in both immediate and long-term ways. The medulla provides the body with an instant burst of readiness, while the cortex sustains a more measured and enduring response. Together, they create a system capable of handling both the sudden emergencies and the slow challenges of life. The adrenal medulla is most famous for secreting adrenaline, also known as epinephrine. When the brain perceives a threat, whether real or imagined, the hypothalamus sends signals through the sympathetic nervous system that reach the adrenal medulla. In response, adrenaline is released into the bloodstream, racing through the body in seconds. This hormone prepares the body for the classic fight-or-flight response. The heart beats faster, blood pressure rises, airways open to take in more oxygen, and glucose is released from the liver to fuel the muscles. Pupils dilate to sharpen vision, and blood flow shifts from the digestive tract to the skeletal muscles, prioritizing action over rest. This state of heightened readiness can make the difference between survival and danger. Yet, once the threat has passed, adrenaline levels fall quickly, and the body returns to balance. Alongside adrenaline, the adrenal medulla secretes noradrenaline, or norepinephrine, which reinforces many of these same effects, particularly on blood vessels and blood pressure. Together, these catecholamines act as swift messengers of alarm, mobilizing resources and focusing the body's energy where it is needed most. The speed of their action is remarkable, reflecting the close partnership between the adrenal medulla and the nervous system. In truth, the adrenal medulla functions almost like an extension of the sympathetic nerves, but with the added power of broadcasting its signals through the bloodstream, reaching every organ in moments. While the medulla acts quickly, the adrenal cortex takes a longer view. It produces steroid hormones that shape metabolism, salt and water balance, and the body's capacity to endure stress. The cortex itself is divided into 3 layers, each producing different hormones. The outermost layer, the zona glomerulosa, secretes mineralocorticoids, the most important of which is aldosterone. Aldosterone acts primarily on the kidneys, promoting the retention of sodium and the excretion of potassium. By conserving sodium, aldosterone also helps the body retain water, maintaining blood pressure and fluid balance. Without aldosterone, the delicate equilibrium of salts and water in the body would falter, leading to dehydration, low blood pressure, and weakness. The middle layer, the zona fasciculata, produces glucocorticoids, with cortisol being the principal hormone. Cortisol is often called the stress hormone because of its central role in helping the body cope with prolonged strain. When stress endures beyond a brief alarm, the hypothalamus releases corticotropin-releasing hormone, prompting the pituitary to secrete adrenocorticotropic hormone, or ACTH. This, in turn, stimulates the adrenal cortex to release cortisol. Once in the bloodstream, cortisol adjusts metabolism to ensure a steady supply of energy. It increases blood sugar by promoting gluconeogenesis in the liver. It helps break down fats and proteins for fuel, and it suppresses processes that are not immediately essential, such as inflammation and certain immune responses. In doing so, cortisol allows the body to conserve resources for the challenge at hand, keeping it resilient even during prolonged difficulty. The innermost layer, the zona reticularis, produces androgens, weak male sex hormones, that supplement those made in the gonads. In men, their contribution is minor compared to testosterone from the testes, but in women, adrenal androgens play a more significant role, influencing body hair growth, libido, and overall hormonal balance. Though less dramatic than cortisol or adrenaline, these hormones remind us that the adrenal glands touch more aspects of life than stress alone, extending into reproduction and secondary sexual traits. The actions of the adrenal glands highlight the dual nature of stress responses. Short-term stress, such as sudden fear or vigorous exercise, relies on adrenaline and noradrenaline. These hormones act like a lightning strike, transforming the body in an instant. Long-term stress, however, such as illness, sustained workload, or emotional strain, depends on cortisol. Cortisol works like a steady flame, ensuring that energy is available and that the body can endure over time. Both are necessary, for life presents both sudden shocks and long challenges, and the adrenal glands are designed to meet both with precision. Yet balance is essential. Too little adrenal activity leads to Addison's disease, a condition where both cortisol and aldosterone are deficient. Symptoms include fatigue, weight loss, low blood pressure, and darkening of the skin. Without treatment, severe adrenal insufficiency can be life-threatening, as the body cannot maintain blood pressure or respond properly to stress. On the other hand, excessive cortisol, as seen in Cushing's syndrome, leads to weight gain, muscle weakness, thinning of the skin, and impaired immunity. Prolonged excess also weakens bones and disrupts metabolism. These conditions reveal the importance of adrenal balance, showing that too much or too little stress hormone undermines health just as surely as stress itself. The adrenal glands also demonstrate the intimate link between mind and body. Emotional experiences, whether anxiety, excitement, or joy, trigger responses in the adrenal hormones. A racing heart before public speaking, a rush of energy during competition, or trembling during fear all bear the fingerprints of the adrenal medulla. Likewise, the strain of long-term worry or illness is mirrored in cortisol's effects, sometimes beneficial, sometimes detrimental. In this way, the adrenal glands are instruments of emotion, translating mental states into physical readiness. Despite their association with stress, the adrenal glands are not organs of alarm alone. They are also organs of adaptation. They allow the body to move between rest and exertion, between calm and strain, without breaking. They are guardians of resilience, ensuring that resources are mobilized when needed and conserved when possible. Their activity is not random, but carefully regulated through feedback loops. Rising cortisol, for instance, signals back to the hypothalamus and pituitary to reduce further release, keeping levels within range. Similarly, blood pressure and salt balance regulate aldosterone, ensuring that water and minerals remain stable. These feedback systems keep the adrenal glands from overwhelming the body, just as they prevent exhaustion from prolonged inactivity. To reflect on the adrenal glands is to recognize the body's remarkable capacity to adapt. In the rush of adrenaline, we see the immediacy of survival. In the steady influence of cortisol, we see the endurance of long struggle. In aldosterone's quiet regulation, we see the importance of balance in the smallest ions. And in the androgens, we see the broader connections to growth, reproduction, and vitality. Each layer, each hormone, contributes to the whole, showing how a pair of small glands can guide the vast spectrum of human experience. As our exploration of the endocrine system continues, the adrenal glands remind us that survival depends not only on food and shelter, but on the body's inner capacity to meet the unpredictable. They are the quiet protectors that rise when life demands more, lending strength, energy, and endurance. When life is calm, they retreat, allowing the body to rest. When life surges with challenge, they awaken, transforming the body into a vessel of readiness. In this rhythm of rise and fall, they ensure that we are not fragile in the face of change but resilient, capable, and enduring. 9. The pineal gland, keeper of sleep. Deep in the brain, nestled between the two hemispheres, in a groove where the thalamic bodies join, lies one of the most mysterious glands in the human body. The pineal gland, a tiny, pinecone-shaped structure, no larger than a grain of rice, has long fascinated philosophers, physicians, and scientists alike. In ancient times, it was thought to be the seat of the soul, a special organ connecting the physical body to the spiritual world. Though modern science views it differently, the pineal gland still holds a certain mystique because of its unique position and its profound influence on the rhythms of life. Today, we understand it as the body's keeper of sleep, a gland that translates the daily cycle of light and darkness into hormonal signals that govern when we feel wakeful and when we feel drowsy. The pineal gland's principal hormone is melatonin, often called the sleep hormone. Melatonin does not induce sleep in the way that a sedative might, but instead signals to the body that night has arrived and it is time to prepare for rest. Its secretion follows a clear rhythm: low during the day when light is abundant, rising in the evening as darkness falls, peaking in the middle of the night, and then declining again toward morning. This daily cycle is deeply tied to the external environment, for light is the master cue that sets the body's clock. The pineal gland therefore acts as an interpreter, translating the language of light into the chemistry of time. The process by which light influences the pineal gland is intricate. Light enters the eyes and strikes specialized receptors in the retina that are sensitive not to shapes or colors, but to brightness. Signals from these receptors travel along a pathway to the suprachiasmatic nucleus of the hypothalamus, often described as the master clock of the brain. From there, messages are relayed to the pineal gland, either stimulating or suppressing melatonin release, depending on the time of day. In bright daylight, the signal suppresses melatonin, keeping us alert. As evening descends and light diminishes, the suppression eases, and melatonin begins to flow, encouraging the body to shift toward rest. In this way, the pineal gland ensures that our internal rhythms remain aligned with the external world. This alignment is crucial for health. Nearly every cell in the body contains its own internal clock, a molecular rhythm that cycles over roughly 24 hours. These clocks regulate metabolism, hormone release, temperature, and countless other processes. Yet without coordination, the body would fall into disorder. The pineal gland, through melatonin, helps synchronize these rhythms, creating coherence across the body. When melatonin rises, it signals to tissues everywhere that night has come, encouraging processes suited to rest and repair. When melatonin falls, it tells the body that it is time for activity and alertness. The harmony of these rhythms underlies our sense of vitality, mood, and well-being. Disruption of the pineal gland's function or of melatonin's cycle can have wide-reaching effects. Jet lag is a familiar example. When we cross time zones quickly, our internal clock remains set to the old time, while the environment signals a new one. The pineal gland, receiving light cues at unfamiliar hours, struggles to adjust melatonin production, leading to fatigue, poor sleep, and disorientation. Shift work produces a similar challenge, as artificial schedules demand wakefulness at night and sleep during the day. Over time, this misalignment can strain the body, increasing the risk of metabolic disorders, mood disturbances, and impaired immunity. These difficulties remind us how deeply our physiology depends on the simple rhythm of light and darkness, and how the pineal gland serves as the bridge between them. Beyond sleep, melatonin has other subtle effects. It is a powerful antioxidant, protecting cells from damage caused by free radicals. It influences immune function, supporting the body's defenses. It may also play roles in regulating reproductive cycles, particularly in animals whose fertility changes with the seasons. In humans, its influence on reproduction is less pronounced but still detectable, with shifts in melatonin levels influencing the timing of puberty, and perhaps even contributing to seasonal mood variations. These wider roles suggest that the pineal gland is not only the keeper of sleep but also a guardian of broader rhythms of health. The pineal gland itself is unique among endocrine organs. Unlike most other glands, it is not shielded by the blood-brain barrier, meaning substances in the bloodstream can reach it more directly. This exposure may reflect its ancient role in sensing the environment and adjusting the body accordingly. The pineal gland also tends to calcify with age, becoming studded with deposits that appear bright on brain scans. While the functional significance of this calcification is still debated, it is one of the reasons the gland has long intrigued scientists. Its location, deep in the brain, yet influenced by the outside world, gives it a special quality, halfway between the inner and outer dimensions of life. Sleep itself, guided by melatonin, is one of the most essential processes for human survival. It allows the brain to consolidate memories, the body to repair tissues, and the immune system to strengthen. During sleep, growth hormone is released, the cardiovascular system finds rest, and energy stores are replenished. Without adequate sleep, concentration falters, mood declines, and health suffers. The pineal gland's quiet signal each evening is therefore not just a reminder of night but an essential step in maintaining life. Its role in orchestrating rest highlights how interconnected the endocrine system is with daily existence, reaching into the very rhythm of waking and sleeping that defines human experience. The history of the pineal gland also reflects humanity's search for meaning in the hidden parts of the body. René Descartes, the 17th century philosopher, speculated that it was the seat of the soul, the place where mind and body met. Though modern science has shown that its role is more biological than mystical, the fascination remains. The pineal gland is still seen by many as a symbol of inner vision, and its location at the center of the brain has lent it an aura of mystery. Yet even in strictly biological terms, it remains remarkable, for a structure so small has the power to influence one of the most fundamental aspects of life, the passage of time itself, as experienced by the body. When we think of the pineal gland, it helps to imagine the quiet descent of evening. As the sun sets and light fades, the pineal begins its work, releasing melatonin into the blood. The body cools slightly, the heart rate slows, and drowsiness sets in. The mind drifts toward dreams, and the repair of the day's wear begins. This process repeats every night, a cycle as old as life itself, binding us to the rotation of the earth and the alternation of day and night. The pineal gland, though silent and unseen, is the faithful timekeeper of this cycle, ensuring that the body finds rest in the darkness and renewal for the coming day. In reflecting on the pineal gland, we are reminded that the body's well-being depends not only on strength and movement, but also on rhythm and rest. Energy without renewal would soon be exhausted. Activity without pause would collapse into disorder. The pineal gland ensures that life does not rush forward without balance, but instead flows in a cycle of wake and sleep, effort and restoration. It is the quiet keeper of sleep, a small guardian of one of life's greatest necessities, guiding us gently into the night and preparing us for the dawn. 10. The gonads, ovaries and testes. Among the endocrine glands, few are as deeply tied to identity, continuity, and the cycles of life as the gonads, the ovaries in females, and the testes in males. They are the organs of reproduction, but their role extends far beyond the generation of new life. Through their hormones, they shape the development of the body, influence behavior, regulate fertility, and sustain the rhythms of reproduction. Their influence is so profound that it touches not only the physical form, but also the emotional and social dimensions of human life. To understand the gonads is to recognize how hormones guide us through the stages of growth, maturity, and the passing on of life's legacy. The testes, located in the scrotum outside the male body cavity, produce sperm, as well as testosterone, the principal male sex hormone. Testosterone begins to exert its influence before birth, guiding the development of male reproductive organs in the fetus. At puberty, its effects become more visible, deepening the voice, increasing muscle mass, broadening the shoulders, and stimulating the growth of facial and body hair. But testosterone does more than shape outward appearance. It sustains the continual production of sperm, maintains libido, and supports bone strength and red blood cell formation. Even in adulthood, its steady presence influences energy, mood, and overall vitality, showing that the testes are not only organs of reproduction, but also guardians of ongoing health. The ovaries, located on either side of the uterus in the female pelvis, produce eggs, as well as the hormones estrogen and progesterone. These hormones, like testosterone, begin their influence early in life but become especially important at puberty. Estrogen stimulates the development of the breasts, the widening of the hips, and the pattern of fat distribution, characteristic of the female body. It also prepares the uterus for potential pregnancy and regulates the menstrual cycle. Progesterone, secreted primarily after ovulation, supports the uterine lining, ensuring it is ready to nourish an embryo if conception occurs. Together, estrogen and progesterone orchestrate the complex cycle of fertility, month by month, guiding the potential for new life. The menstrual cycle is one of the most remarkable examples of hormonal coordination in the human body. Lasting about 28 days on average, it is divided into phases marked by the rise and fall of ovarian hormones. In the first half of the cycle, estrogen gradually increases, stimulating the growth of the uterine lining and preparing an egg to mature. Around the midpoint, a surge of luteinizing hormone from the pituitary triggers ovulation, the release of an egg from the ovary. After ovulation, progesterone levels rise, stabilizing the uterine lining in case of implantation. If no pregnancy occurs, hormone levels fall, the lining is shed as menstruation, and the cycle begins anew. This rhythm continues month after month, a testament to the finely tuned dialogue between the ovaries and the brain. The gonads also highlight the principle of feedback regulation. The hypothalamus releases gonadotropin-releasing hormone, prompting the pituitary to secrete luteinizing hormone and follicle-stimulating hormone. These in turn act on the ovaries and testes, stimulating the production of sex hormones and gametes. Rising levels of estrogen, progesterone, and testosterone feed back to regulate the hypothalamus and pituitary, creating cycles of stimulation and restraint. This feedback not only maintains balance, but also allows for the rhythmic patterns of fertility in women and the steady production of sperm in men. The effects of gonadal hormones extend beyond reproduction. Estrogen, for example, has protective effects on the cardiovascular system, promoting healthy blood vessels and influencing cholesterol levels. It also supports bone strength, helping to prevent osteoporosis. Progesterone contributes to mood regulation and has calming effects on the nervous system. Testosterone influences not only physical strength but also confidence, competitiveness, and drive. These broader effects remind us that hormones are never confined to one purpose. They ripple outward, influencing body and mind in ways both subtle and profound. Changes in gonadal hormones across the lifespan illustrate their importance. In childhood, their levels are relatively low, allowing the body to grow without the influence of sexual development. At puberty, hormone levels surge, transforming the body into its adult form and awakening fertility. In women, hormone levels fluctuate with each menstrual cycle, creating monthly rhythms that continue through the reproductive years. Eventually, in midlife, the ovaries reduce their production of estrogen and progesterone, leading to menopause. This transition brings an end to fertility, but also changes in bone density, metabolism, and mood, reflecting the wide-ranging influence of ovarian hormones. In men, testosterone levels decline more gradually with age, sometimes leading to reduced muscle mass, lower energy, and changes in libido. These shifts reveal how deeply hormones shape not only reproduction but the overall experience of aging. Disorders of the gonads further underscore their significance. In women, conditions such as polycystic ovary syndrome disrupt normal hormone production, leading to irregular cycles, infertility, and metabolic changes. In men, low testosterone can cause fatigue, reduced muscle strength, and diminished fertility. Both sexes may face challenges with hormonal imbalances that affect not only reproductive health but also emotional well-being and long-term vitality. These conditions remind us of the delicate balance required for health and the interconnectedness of hormones with every aspect of life. Yet the gonads are not organs of biology alone. They are also tied to the human experience of love, partnership, and continuity. The hormones they produce influence not only physical readiness for reproduction, but also emotional states, attraction, and bonding. Oxytocin from the hypothalamus and estrogen from the ovaries, for example, interact to strengthen the bonds between parent and child, while testosterone and dopamine play roles in attraction and desire. In this way, the gonads are part of a larger symphony of hormones that support not only survival but also connection and the continuation of the human story. To reflect on the ovaries and testes is to recognize the cycles of life itself. They are the organs that allow the passage of traits from one generation to the next, but they also shape the bodies and experiences of individuals across their own lifetimes. From the awakening of puberty to the rhythms of adulthood and the transitions of aging, the gonads mark the passage of time in ways that are both deeply personal and universally human. They remind us that life is not only about the survival of the individual but also about continuity, the weaving of one life into the fabric of another. The gonads, like all endocrine organs, perform their work in silence. We do not feel the release of estrogen, progesterone, or testosterone in the moment they occur. Yet their influence unfolds steadily, sculpting bodies, guiding reproduction, and shaping emotions. They are the stewards of growth, fertility, and legacy, ensuring that life not only persists but flourishes. In their quiet way, they remind us that the story of hormones is not merely about chemistry but about the cycles of life, love, and continuity carried forward through time. 11. Growth hormone and development. Among the many messengers of the endocrine system, carry as profound an influence on the shaping of the human body as growth hormone, secreted by the anterior lobe of the pituitary gland. This single substance guides the lengthening of bones, the strengthening of muscles, and the overall expansion of the body from infancy through adolescence. Its effects, however, are not confined to the early years of life. Growth hormone continues to play a role throughout adulthood, supporting metabolism, repairing tissues, and maintaining the balance of body composition. It is the hormone of development, but also the hormone of renewal, ensuring that the body not only grows, but also endures. Growth hormone is released in pulses, often highest at night during deep sleep. This rhythm highlights the close connection between rest and growth, a truth long observed in the way children seem to grow taller during nights of sound sleep. The secretion of growth hormone is stimulated by growth hormone-releasing hormone from the hypothalamus and inhibited by somatostatin, another hypothalamic hormone. Once released into the bloodstream, growth hormone travels to many tissues, but one of its principal targets is the liver, where it stimulates the production of insulin-like growth factor 1, or IGF-1. This substance then carries forward many of the growth-promoting effects, acting on bones, muscles, and organs to encourage cell division, protein synthesis, and the accumulation of tissues. The influence of growth hormone on bones is especially striking. During childhood and adolescence, it stimulates the elongation of long bones through their growth plates, the regions of cartilage at their ends. Under the combined influence of growth hormone and IGF-1, these plates expand, gradually being replaced by bone tissue as the skeleton lengthens. This process continues until the growth plates close in late adolescence, marking the end of height increase. Without growth hormone, bones would remain stunted, and the body would not reach its full stature. With excessive growth hormone during youth, the skeleton may grow excessively tall, producing the condition known as gigantism. In adulthood, when the growth plates have closed, growth hormone no longer increases height, but it still influences bone by maintaining density and strength. Too little hormone in this stage may contribute to frailty, while too much leads to acromegaly, a condition in which bones and tissues thicken abnormally, altering the shape of the face, hands, and feet. Muscles are also deeply shaped by growth hormone. It stimulates protein synthesis, encouraging muscle fibers to grow larger and stronger. It also mobilizes fat stores, providing energy for muscle activity and reducing the reliance on protein breakdown. In this way, growth hormone supports lean body mass, balancing the proportions of muscle and fat. Athletes and those seeking to enhance performance have long been tempted by synthetic growth hormone, though its misuse carries risks. In natural physiology, however, the hormone is carefully regulated, rising and falling in harmony with sleep, nutrition, and activity. Metabolism is another realm in which growth hormone exerts its influence. It increases the breakdown of fat, releasing fatty acids into the blood as an energy source. It reduces the use of glucose by cells, conserving it for organs that rely heavily on sugar, such as the brain. It also supports the synthesis of proteins, ensuring that tissues can be repaired and renewed. In times of fasting or stress, growth hormone plays a protective role, maintaining blood sugar levels and preventing muscle breakdown. These actions highlight its role not only in growth but in adaptation, guiding the body through the fluctuations of daily life. The secretion of growth hormone is highest during childhood and adolescence, the periods of rapid physical development. It then declines gradually with age, a change that may contribute to the reduced muscle mass, increased fat, and slower tissue repair, often observed in older adults. Some researchers have explored the idea of supplementing growth hormone in aging, but the natural decline may reflect a balance that the body has evolved to maintain. Too much hormone in later life carries risks, just as too little does. The lesson is once again one of balance. with the body adjusting hormone levels according to stage of life. Growth hormone does not act alone. Its effects are intertwined with those of other hormones, particularly thyroid hormones, sex hormones, and insulin. Thyroid hormones provide the metabolic support necessary for growth, ensuring that cells have the energy to divide and mature. Estrogen and testosterone, rising during puberty, interact with growth hormone to drive the dramatic changes of adolescence, accelerating height increase, but also contributing to the eventual closure of growth plates. Insulin, meanwhile, supports the storage of nutrients, allowing growth hormone and IGF-1 to use them effectively. This cooperation reveals the complexity of growth, a process not directed by one messenger, but by a chorus of signals working in harmony. Disorders of growth hormone reveal the magnitude of its influence. In children, deficiency leads to short stature, delayed development, and sometimes other health challenges. With treatment, often involving synthetic growth hormone, normal growth can often be restored. In adults, deficiency may result in fatigue, reduced muscle mass, increased fat, and fragile bones. Conversely, excess secretion from a pituitary tumor may lead to gigantism in children or acromegaly in adults, both conditions with significant health consequences. These examples remind us that the delicate regulation of growth hormone is essential, and when disrupted, the balance of the entire body is affected. Beyond its physical effects, growth hormone also shapes the sense of vitality. Individuals with adequate levels often describe feeling more energetic, resilient, and strong, while those with deficiencies may struggle with fatigue and weakness. This subjective quality suggests that hormones do not only shape the body's structures but also influence the lived experience of health. Growth hormone, by supporting metabolism and tissue renewal, contributes to the sense of aliveness that carries people through their daily lives. The rhythm of growth hormone release, highest at night, ties it closely to sleep. Deep sleep is a time when the body repairs itself, tissues are restored, and growth hormone pulses into the bloodstream. This link explains why poor sleep in children may impair growth, and why adequate rest is important at every stage of life. It also illustrates the broader truth that hormones are not isolated events but part of daily cycles, intertwined with behaviors such as sleeping, eating, and moving. The pineal gland, with its melatonin, and the pituitary, with its growth hormone, work in concert to ensure that night is not wasted but used for renewal. Reflecting on growth hormone invites us to see development not as a simple matter of size, but as a lifelong process of building, maintaining, and adapting. In childhood, it allows the body to reach its intended stature. In adolescence, it partners with other hormones to sculpt the adult form. In adulthood, it sustains tissues, supports metabolism, and aids recovery from stress. In aging, its gradual decline shifts the body toward conservation rather than expansion. At every stage, it is present, sometimes dramatic, sometimes subtle, but always guiding the body forward. In the grand story of the endocrine system, growth hormone represents the theme of becoming. It is the force that moves the body from small to large, from fragile to strong, from child to adult. But it also represents the theme of resilience, sustaining repair and vitality long after growth has ceased. To contemplate growth hormone is to contemplate life itself as a process of continuous building and renewal. Its pulses in the night are like quiet reminders that the body is never still but always moving, always shaping itself, always preparing for the day to come. 12. Hormones and metabolism. Metabolism is the quiet flame that sustains life, the sum of countless chemical reactions occurring in every cell, every moment of the day. It is the process by which food is transformed into energy, by which molecules are built up into tissues or broken down into fuel, and by which balance is maintained between storage and use. The endocrine system, through its hormones, is one of the central regulators of this flame. Without hormonal control, metabolism would flicker erratically, sometimes burning too quickly, sometimes slowing into dangerous stillness. Instead, hormones keep it steady, adjusting to the needs of the body in each moment. From rest to exertion, from fasting to feasting. At the heart of metabolic regulation lies the thyroid gland, whose hormones, thyroxine and triiodhyronin, determine the general pace of metabolism. These hormones increase oxygen consumption in cells, stimulate the production of enzymes, and enhance the activity of mitochondria, the powerhouses that generate energy. A person with normal thyroid function may never notice this constant background influence. But when thyroid hormones fall short, metabolism slows dramatically. Fatigue, weight gain, and cold intolerance become evident, while an excess of thyroid hormones accelerates metabolism to the point of restlessness, weight loss, and heat sensitivity. The thyroid thus acts as a kind of master switch, setting the tempo of metabolic processes throughout the body. Insulin, secreted by the pancreas, is another essential regulator. After a meal, when glucose enters the blood from digested food, insulin rises to usher this sugar into cells. In the liver, glucose is stored as glycogen. In muscles, it is taken up to provide fuel for contraction. In fat tissue, it is converted to triglycerides for long-term storage. Insulin, therefore, shifts metabolism into a state of storage and building, ensuring that nutrients are saved for later use. Without insulin, glucose remains in the bloodstream, leaving cells starved of energy, even as blood sugar rises dangerously high. The result is diabetes, a condition that illustrates vividly the importance of insulin to metabolic balance. Balancing insulin is glucagon, also from the pancreas, which exerts its effects during fasting or between meals. Glucagon signals the liver to break down glycogen into glucose and to synthesize new glucose from other substrates. Its action ensures that blood sugar does not fall too low, protecting the brain, which depends on a continuous supply of glucose. This interplay between insulin and glucagon reflects the broader principle of metabolic balance: storage and release, conservation and mobilization, always adjusting to keep energy available without waste or deficiency. Cortisol, produced by the adrenal cortex, adds another dimension to this regulation. Known as a stress hormone, cortisol mobilizes energy during times of prolonged challenge. It stimulates gluconeogenesis, increases blood sugar, and promotes the breakdown of fat and protein for fuel. Cortisol also dampens processes not immediately necessary for survival, such as inflammation or reproduction, conserving energy for the demands of stress. Though often maligned, cortisol is essential in moderation, ensuring that the body can endure strain and maintain energy supply when demands extend beyond the short term. Growth hormone, secreted in pulses by the pituitary gland, also shapes metabolism. It stimulates fat breakdown, spares glucose for essential organs, and encourages protein synthesis. Its effects are especially evident during childhood and adolescence, when the body is growing rapidly, but they continue into adulthood as well, supporting tissue maintenance and adaptation. Growth hormone demonstrates that metabolism is not only about energy but also about building, the creation of new tissues to replace the old. Sex hormones, too, influence metabolism in subtle yet important ways. Testosterone supports muscle mass and promotes the burning of fat, giving the male body a higher proportion of lean tissue. Estrogen helps regulate fat distribution in the female body, favoring storage around the hips and thighs. And it also supports bone health and cardiovascular function. As these hormones decline with age, changes in metabolism become evident, with shifts in fat distribution, muscle mass, and overall energy. These transitions remind us that hormones and metabolism are deeply intertwined with the stages of life. Another key player is leptin, a hormone secreted by fat cells themselves. Leptin communicates with the brain about the state of energy reserves in the body. When fat stores are sufficient, leptin levels rise, signaling satiety and reducing appetite. When fat stores decline, leptin falls, increasing hunger and promoting energy conservation. This feedback ensures that energy balance is maintained over the long term. Aligning food intake with energy needs. Ghrelin, secreted by the stomach, plays the opposite role, rising before meals to stimulate appetite and falling afterward. Together, leptin and ghrelin form part of the hormonal dialogue between the body and the brain, guiding eating behavior and energy expenditure. Metabolism is not a fixed process, but one that adapts to circumstances. During fasting, the body shifts from burning glucose to burning fat, a transition orchestrated by falling insulin, rising glucagon, and the influence of cortisol and growth hormone. During prolonged exercise, adrenaline from the adrenal medulla mobilizes glucose and fat, ensuring muscles have the fuel they need. After a meal, insulin dominates, storing nutrients for future use. These transitions occur seamlessly, guided by hormones that adjust the flame of metabolism moment by moment. Disorders of metabolism reveal the consequences of hormonal imbalance. Diabetes, hypothyroidism, Cushing's syndrome, and metabolic syndrome all involve disruptions in hormonal regulation, leading to fatigue, weight changes, and long-term health risks. Even conditions such as obesity are influenced not only by diet and activity, but by the interplay of hormones like leptin, insulin, and cortisol. These disorders show that metabolism is not simply about calories in and calories out, but about the body's complex hormonal orchestration of how energy is used, stored, and conserved. The link between metabolism and circadian rhythms is another reminder of the pineal gland's role in setting the stage for hormonal action. Metabolic processes vary with the time of day, with insulin sensitivity higher in the morning and fat metabolism more active at night. Melatonin from the pineal gland, cortisol from the adrenal glands, and growth hormone pulses during sleep all influence these rhythms, aligning metabolism with the cycles of light and darkness. This coordination ensures that the body uses energy efficiently, supporting both activity during the day and repair during the night. Reflecting on hormones and metabolism invites us to see energy not as a simple commodity, but as a dynamic flow, constantly adjusted to sustain life. Hormones are the regulators of this flow, ensuring that energy is available when needed, stored when abundant. They embody the principle of balance, guiding the body between feast and fast, activity and rest, growth and conservation. Metabolism is life's quiet flame, and hormones are the keepers of its steadiness. Through their constant adjustments, they allow us to move, to think, to grow, and to rest, without ever being aware of the complexity beneath the surface. Without them, the flame would flicker and die. With them, it burns steadily, carrying us forward through each day and each night, sustaining the continuity of life. 13. Hormones and mood. Mood is one of the most delicate and complex aspects of human life. It is the quiet undercurrent that shapes how the world feels, how we respond to challenges, and how we experience joy, calm, or sadness. Though it often seems like an intangible quality of the mind, mood is deeply rooted in the body's chemistry. Hormones, circulating silently through the bloodstream, they interact with the brain's neurotransmitters, alter the sensitivity of receptors, and shift the balance of calmness, energy, and connection. In this way, the endocrine system not only regulates growth, metabolism, and reproduction, but also touches the very essence of how life feels from within. One of the most well-known hormones linked to mood is serotonin. Though technically classified as a neurotransmitter, serotonin is also influenced by hormones that regulate its production and function. Serotonin is often associated with feelings of contentment and well-being, and when its levels are low, individuals may experience depression, anxiety, or irritability. The production of serotonin is influenced by melatonin, the hormone of the pineal gland that governs sleep. A lack of restful sleep can disrupt serotonin levels, contributing to mood disturbances. This interconnection shows how tightly mood is woven into the rhythms of daily life, with sleep, light, and hormones all combining to create emotional stability. Dopamine is another chemical closely tied to mood, particularly to motivation, reward, and pleasure. It is influenced by hormones such as testosterone and estrogen, which can enhance sensitivity to dopamine's effects. This is one reason why fluctuations in sex hormones, such as those occurring during puberty, the menstrual cycle, or menopause, can alter mood and motivation. Dopamine's role in reward explains why hormonal imbalances sometimes manifest as changes in drive or enthusiasm, while balanced hormones support a sense of purpose and satisfaction. Oxytocin, often called the bonding hormone, plays a unique role in shaping emotional states. Produced in the hypothalamus and released from the posterior pituitary, oxytocin is most famous for its role in childbirth and nursing, but its effects extend far beyond reproduction. It fosters feelings of trust, attachment, and social connection. During moments of intimacy, friendship, or even shared laughter, oxytocin rises, reinforcing bonds and creating a sense of belonging. In this way, hormones influence not only individual mood but also the emotional fabric of human relationships, showing that connection and cooperation are deeply biological as well as social. Cortisol, the hormone of stress, is another powerful player in mood regulation. In short bursts, cortisol can increase alertness and sharpen focus, providing the energy to respond to challenges. But when cortisol remains elevated for too long, as in chronic stress, it begins to wear on the mind. Persistent high levels can contribute to anxiety, irritability, and even depression. The hippocampus, a part of the brain involved in memory and emotion, is particularly sensitive to cortisol, and prolonged exposure can impair its function. This explains why long-term stress often leads not only to physical strain but also to emotional fatigue, forgetfulness, and difficulty maintaining a positive outlook. Sex hormones also shape mood in important ways. Estrogen, for example, has a stabilizing effect on mood, partly by influencing serotonin and dopamine. Fluctuations in estrogen, such as those occurring during the menstrual cycle, can lead to changes in emotional state. Some women experience premenstrual syndrome, where shifts in hormones contribute to irritability, sadness, or anxiety. Progesterone, another ovarian hormone, has calming properties, often creating a sense of relaxation in the luteal phase of the cycle. Testosterone, meanwhile, can influence confidence, energy, and assertiveness. Both very high and very low levels of testosterone can alter mood, highlighting again the importance of balance rather than abundance. Thyroid hormones also influence mood. When thyroid activity is low, as in hypothyroidism, individuals often report feelings of fatigue, sadness, or lack of motivation. When thyroid activity is excessive, as in hyperthyroidism, mood can swing toward nervousness, restlessness, or irritability. These effects are so pronounced that thyroid function is often checked when mood disorders are suspected, showing that emotional states cannot be separated from the chemistry of the body. Adrenaline and noradrenaline, the hormones of the adrenal medulla, influence mood as well, though in a more immediate way. Their surges create feelings of excitement, anxiety, or heightened alertness. While brief increases can be exhilarating, prolonged activation can contribute to chronic anxiety or nervous tension. Their effects demonstrate how mood can shift rapidly with changes in hormone levels, moving from calm to alert in an instant. The relationship between hormones and mood is bidirectional. Just as hormones shape emotions, emotions influence hormones. Stressful thoughts can trigger the release of cortisol. Feelings of safety and affection can increase oxytocin. The body and mind are in constant conversation, with hormones serving as one of the main bridges between them. This interplay ensures that emotional states are reflected in physical readiness, and that physical changes in turn influence the inner landscape of feelings. Life stages illustrate these influences clearly. During adolescence, the surge of sex hormones reshapes not only the body, but also emotional life, contributing to the intensity and variability of teenage moods. During pregnancy, the rise in estrogen and progesterone supports the development of new life, but also alters emotional states, sometimes creating feelings of serenity, sometimes of vulnerability. After childbirth, the sudden drop in these hormones can contribute to mood swings or postpartum depression. Later in life, the decline of sex hormones during menopause and andropause can bring changes in mood, energy, and outlook. Each transition shows how hormones guide not only physical changes but emotional experiences as well. Disorders of mood often reflect disruptions in hormonal balance. Depression may be linked to abnormalities in cortisol regulation, thyroid hormones, or sex hormones. Anxiety may be exacerbated by overactive stress hormones. Even seasonal affective disorder, a form of depression occurring in winter months, is tied to changes in melatonin and serotonin linked to reduced light. These conditions reveal that mood cannot be understood in isolation from the body's chemistry, and that hormonal harmony is a foundation of emotional well-being. Yet hormones are not dictators of mood. They are partners. They provide the chemical background against which thoughts, experiences, and relationships play out. A surge of oxytocin may foster feelings of trust, but the presence of a loved one gives that trust its meaning. A rise in dopamine may create motivation, but it is the pursuit of goals that gives motivation direction. Hormones shape the canvas, but life paints the picture. Reflecting on hormones and mood reminds us that emotions, though intangible, are deeply embodied. The warmth of affection, the sharpness of fear, the calm of contentment, and the heaviness of sadness all arise from a dialogue between the mind and the body's chemistry. Hormones are the subtle guides of this dialogue, shifting tone and balance, ensuring that emotions flow with the rhythms of life. In the grand symphony of the endocrine system, mood is one of the most delicate melodies. It is shaped by many instruments: serotonin, dopamine, oxytocin, cortisol, estrogen, testosterone, thyroid hormones, and more, each contributing its own note. When they are in harmony, the melody is balanced, creating a sense of stability and well-being. When they fall out of tune, the melody becomes discordant, manifesting as sadness, anxiety, or instability. Yet just as music can shift and resolve, so too can hormones and mood find their way back into balance. The story of hormones and mood is ultimately a story of connection between body and mind, between individuals, and between the inner world of feelings and the outer world of physiology. To contemplate this story is to recognize that emotions are not fleeting illusions but integral parts of life, grounded in the body's chemistry yet elevated by the human experience. Hormones, in their quiet way, remind us that mood is both biology and poetry, both signal and song, carrying us through the changing landscape of each day. 14. Hormones and stress adaptation. Stress is one of the most universal aspects of life. It is not only the dramatic stress of sudden danger or emotional upheaval, but also the quieter, persistent stresses of daily living, the body adapting to cold weather, or managing the ordinary challenges of work and responsibility. Stress is, at its core, the demand placed on the body to adjust. The endocrine system, through its hormones, plays a central role in this adjustment, guiding the body to respond, endure, and eventually recover. Hormones help transform stress from something overwhelming into something manageable, allowing the body to remain balanced even in the face of change. When stress arises suddenly, the adrenal medulla responds first by releasing adrenaline and noradrenaline. These hormones act within moments, increasing heart rate, raising blood pressure, dilating airways, and mobilizing glucose. The fight-or-flight response is one of the most visible demonstrations of hormones at work, preparing the body to take action. Yet this response is not limited to life-threatening events. Even everyday moments, a sudden loud noise, the anticipation of speaking in public, the thrill of competition, trigger similar hormonal surges. Adrenaline makes us alert, sharp, and ready, ensuring that the body can respond quickly to immediate challenges. If stress continues beyond those first moments, the adrenal cortex takes over, releasing cortisol. Cortisol is slower to rise than adrenaline, but its effects are longer lasting. It ensures that energy supplies remain steady, even when the body must endure hours or days of strain. Cortisol stimulates the liver to produce glucose, mobilizes fats and proteins for fuel, and suppresses processes that are less urgent, such as digestion or inflammation. This shift conserves resources, channeling energy toward coping with the stressor. Cortisol is thus the hormone of adaptation, allowing the body not only to react, but to sustain its response over time. The hypothalamic pituitary adrenal axis lies at the heart of this adaptation. When the brain perceives stress, the hypothalamus releases corticotropin-releasing hormone, which prompts the pituitary gland to secrete adrenocorticotropic hormone. This, in turn, stimulates the adrenal cortex to release cortisol. Rising cortisol then feeds back to the hypothalamus and pituitary to prevent overproduction, creating a cycle of regulation. This axis ensures that cortisol levels rise when needed and fall when the stress has passed, preserving balance. It is a system designed for precision, protecting the body from both deficiency and excess. Short-term stress, guided by these hormones, is not harmful. In fact, it can be beneficial, sharpening focus, enhancing memory, and mobilizing strength. It is one reason why people often perform well under pressure, drawing on reserves they might not have realized they possessed. The surge of adrenaline sharpens the senses, while cortisol sustains energy for the task. In nature, these mechanisms have clear survival value, allowing an animal to escape a predator, endure harsh weather, or recover from injury. For humans, they are equally vital, though the stressors may be social, emotional, or intellectual, as much as physical. The challenge arises when stress becomes chronic. Prolonged elevation of cortisol can strain the body, leading to fatigue, impaired immunity, disrupted sleep, and mood disturbances. The hippocampus, an area of the brain important for memory and learning, is particularly sensitive to cortisol, and chronic stress can diminish its function. This may explain why long-term stress often makes it difficult to concentrate or recall information. Excess cortisol can also weaken bones, increase abdominal fat, and contribute to cardiovascular risk. In this way, hormones that are protective in the short term can become harmful if stress never resolves. The body does, however, have mechanisms for recovery. When stress diminishes, cortisol levels fall, adrenaline declines, and the parasympathetic nervous system restores calm. Hormones such as oxytocin and endorphins rise, promoting feelings of safety, relaxation, and even pleasure. This shift demonstrates the body's resilience, its ability to return to balance after strain. The alternation between stress and recovery is essential. Just as muscles grow stronger by alternating exertion with rest, so too does the endocrine system thrive by balancing periods of activation with periods of calm. Different life stages reveal variations in stress responses. Children often have more flexible stress systems, recovering quickly after challenges. Adolescents, with their surging sex hormones, may experience stress more intensely, reflecting the interplay between reproductive hormones and cortisol. Adults balance stress responses with the responsibilities of life, sometimes carrying chronic burdens that tax the system. Older adults may experience altered cortisol rhythms, sometimes with higher levels at night, contributing to disrupted sleep. These changes highlight that stress adaptation is not fixed, but shifts across the lifespan, always reflecting the interplay of hormones, environment, and experience. Not all hormones act in isolation in stress adaptation. Growth hormone, for example, rises during stress, helping to mobilize energy and repair tissues. Prolactin also increases, influencing immune function, and possibly offering protection during strain. Even thyroid hormones play a role, as metabolism adjusts to stress demands. This web of interactions shows that stress is not a single pathway but a symphony of hormonal responses, each contributing to the body's capacity to cope. The link between stress and reproduction is particularly striking. High levels of cortisol can suppress the release of gonadotropin-releasing hormone from the hypothalamus, leading to reduced fertility. This makes biological sense, as the body prioritizes survival over reproduction in times of hardship. Similarly, stress can delay puberty, alter menstrual cycles, or reduce testosterone levels. These effects remind us that the endocrine system is unified, with hormones from one gland influencing many others, always adapting the whole body to its circumstances. The story of stress adaptation is not only one of biology, but also of experience. Hormones respond not only to physical threats, but also to thoughts, expectations, and perceptions. Worry about the future, even in the absence of danger, can activate the same hormonal cascades as actual events. Conversely, feelings of safety, belonging, and trust can quiet the stress response. This illustrates the profound connection between mind and body, with hormones as the mediators of that connection. Despite the challenges of chronic stress, the resilience of the hormonal system is remarkable. Practices that promote calm, restful sleep, steady breathing, gentle movement, and supportive relationships allow oxytocin, serotonin, and endorphins to rise, counterbalancing cortisol and adrenaline. These hormones create feelings of relaxation and connection, demonstrating that the endocrine system is not only about responding to threats, but also about fostering peace. Balance emerges not from eliminating stress, which is impossible, but from ensuring that recovery follows activation. Reflecting on hormones and stress adaptation reveals the wisdom of the body. It is not built to avoid strain, but to endure it, to respond swiftly, to sustain effort, and to recover with calm. Adrenaline and cortisol may be the most visible actors, but they are supported by a chorus of other hormones, each adjusting metabolism, immunity, reproduction, and mood. Together, they ensure that stress is not destructive but adaptive, a force that strengthens as well as challenges. In the end, hormones remind us that stress is not an enemy but a teacher. It reveals the body's capacity to rise to occasions, to find strength in difficulty, and to restore balance afterward. The endocrine system, through its hormones, transforms stress into resilience, ensuring that life's challenges are not only endured but woven into the story of growth. Just as a tree bends in the wind but does not break, so too does the body, guided by its hormones, adapt and endure. 15. Daily rhythms and seasonal cycles. Life is not constant. It flows with patterns, rises and falls with time, and is guided by cycles that extend from the scale of hours to the span of seasons. Within the human body, these cycles are orchestrated not by clocks on the wall or calendars in the hand, but by hormones that ebb and flow with remarkable precision. The endocrine system, working in concert with the nervous system, ensures that the body is aligned with the passage of time, adjusting metabolism, energy, mood, and rest to the daily rotation of the earth and the changing rhythm of the year. These daily rhythms and seasonal cycles form one of the quiet foundations of life, weaving human existence into the fabric of nature itself. The most familiar of these rhythms is the circadian rhythm, a cycle of roughly 24 hours that governs sleep and wakefulness, hunger and satiety, alertness and rest. At the heart of this rhythm is the suprachiasmatic nucleus of the hypothalamus, the brain's master clock. This tiny cluster of neurons receives information about light from the eyes and uses it to coordinate the body's internal processes. The pineal gland, through its release of melatonin, plays a crucial role in carrying this signal throughout the body. As darkness falls, melatonin levels rise, preparing the body for rest. As dawn arrives and light returns, melatonin falls, lifting wakefulness and alertness. This simple cycle of light and darkness ripples into every tissue, aligning metabolism, hormone release, and even immune function with the time of day. Cortisol, often called the stress hormone, also follows a circadian rhythm. Its levels peak in the early morning, just before waking, providing energy and alertness for the day ahead. As the day progresses, cortisol levels decline, reaching their lowest point during the night. This rhythm helps align energy availability with daily activity and allows the body to rest when it is time for sleep. Disruption of this rhythm, whether through shift work, jet lag, or chronic stress, can lead to fatigue, mood disturbances, and impaired health, reminding us how deeply life depends on alignment with natural cycles. Other hormones also follow daily patterns. Growth hormone is released in pulses, with its largest surge occurring during deep sleep in the early part of the night. This ties tissue repair and renewal to rest, ensuring that the body rebuilds itself when activity is low. Insulin sensitivity varies throughout the day, often highest in the morning, reflecting the body's anticipation of energy needs. Even reproductive hormones can fluctuate with daily rhythms, showing that the influence of time extends into every aspect of life. Beyond daily cycles are the longer rhythms of infradian cycles, which last longer than 24 hours. The menstrual cycle in women is one of the most well-known examples, lasting about 28 days and governed by the ebb and flow of estrogen, progesterone, luteinizing hormone, and follicle-stimulating hormone. This cycle is not only about reproduction but also about shifts in mood, energy, and metabolism, reminding us that hormones are not confined to single functions but influence the whole experience of life. Seasonal cycles are another example, shaped by changes in light and environment across the year. In many animals, these cycles guide reproduction, migration, or hibernation. In humans, they are subtler, but still present, influencing mood, immunity, and perhaps even fertility. Seasonal affective disorder is a clear demonstration of how seasonal changes influence hormones. In winter months, when daylight is shorter, melatonin secretion may extend longer into the morning, contributing to fatigue and low mood. Reduced light also affects serotonin, a neurotransmitter linked to well-being, leading to feelings of sadness or lethargy. The treatment for this condition often involves light therapy, which restores the natural cues that the pineal gland uses to regulate cycles. This shows how closely human physiology remains tied to the environment. Even in modern times, when artificial light and technology might seem to separate us from nature, the interplay between daily and seasonal rhythms creates a rich tapestry of hormonal patterns. Cortisol, melatonin, growth hormone, and reproductive hormones all rise and fall according to both the hour and the season. This orchestration ensures that the body not only responds to immediate needs but also prepares for the broader context of life. For example, immune activity tends to be stronger during certain seasons, perhaps reflecting the evolutionary need to defend against infections that are more common in winter. Energy metabolism also shifts subtly with the seasons. aligning the body with cycles of food availability that were once critical to survival. The disruption of these rhythms can have profound effects on health. Shift work, which forces individuals to be awake at night and sleep during the day, misaligns hormonal cycles from the natural rhythm of light and darkness. This misalignment is associated with increased risks of obesity, diabetes, cardiovascular disease, and mood disorders. Jet lag, though temporary, provides a glimpse into this disruption, with fatigue, poor concentration, and mood changes arising when the body's internal clock is out of sync with the external environment. These examples highlight the importance of synchrony, the alignment of inner rhythms with outer cycles, yet the body is remarkably adaptable. Over time, the circadian system can adjust to new light cues, shifting melatonin and cortisol rhythms to align with altered schedules. This adaptability reflects the resilience of the endocrine system, which is designed not only for stability but also for adjustment. The pineal gland, the hypothalamus, and the adrenal glands all work together to ensure that life can continue smoothly, even when the environment changes. The beauty of daily rhythms lies in their subtlety. We rarely notice the rise of cortisol in the morning or the surge of melatonin at night, yet we feel their effects in the ease of waking, the clarity of alertness, the calm of evening, and the descent into sleep. These rhythms create a sense of order, a quiet structure underlying the flow of days and nights. They link human life to the turning of the earth, reminding us that biology is not separate from nature but an expression of it. Seasonal cycles extend this connection further, linking us to the broader movements of the planet around the Sunday. The longer nights of winter, the bright mornings of summer, the shifting balance of light and darkness all influence the body's chemistry. Though modern life often shelters us from these changes, the body remains tuned to them, carrying forward an ancient rhythm that has shaped life for millennia. Reflecting on daily rhythms and seasonal cycles reveals that time itself is a biological force. Hormones are the language through which the body keeps time, translating light and darkness, day and night, season and year into physiology and experience. This translation ensures that we rest when the world is dark, awaken when it is light, and adjust to the larger patterns of nature. It is a reminder that life is not only about structure and function, but also about rhythm and flow, a dance between the body and the environment. In the story of the endocrine system, rhythms are as important as the glands themselves. Without cycles, hormones would lose their context. Without timing, signals would lose their meaning. The pineal gland's melatonin, the adrenal gland's cortisol, the pituitary's growth hormone, and the ovaries' estrogen all follow patterns that give coherence to life. These rhythms guide us gently through each day and season, ensuring that life does not unfold in chaos but in harmony with the turning world. 16. Hormones and reproduction in depth. Reproduction is one of the central themes of life, a process through which the continuity of species is ensured and the future is carried forward. In humans, reproduction is not only a matter of biology, but also of intimacy, family, and the rhythms of society. At the heart of this process lies the endocrine system, whose hormones orchestrate the maturation of reproductive organs, the cycles of fertility, the preparation for pregnancy, and the nurturing of new life. Hormones provide the signals that guide the body from childhood to sexual maturity, sustain reproductive capacity through the adult years, and adapt physiology during the extraordinary journey of pregnancy and childbirth. To explore hormones and reproduction in depth is to see how the endocrine system weaves together development, continuity, and care. The story begins in early life, when reproductive organs are present but largely dormant. The hypothalamus, pituitary, ovaries, and testes form a network known as the hypothalamic-pituitary gonadal axis. But in childhood, this axis is relatively quiet. With the onset of puberty, however, it awakens, and hormones surge to initiate the transformation from child to adult. The hypothalamus begins releasing gonadotropin-releasing hormone impulses, stimulating the pituitary to secrete luteinizing hormone and follicle-stimulating hormone. These, in turn, act on the gonads, awakening the testes in males and the ovaries in females. The testes begin producing testosterone, and the ovaries begin producing estrogen and progesterone. These hormones sculpt the adult body, guiding the development of secondary sexual characteristics and preparing the individual for reproductive function. In males, testosterone stimulates the growth of facial and body hair, deepens the voice, increases muscle mass, and supports the production of sperm. The testes continue to generate sperm throughout life, a process sustained by the steady action of follicle-stimulating hormone and testosterone. The male reproductive system thus operates with relative continuity, producing millions of sperm each day in a process that reflects endurance and consistency. Hormones maintain this process quietly, ensuring that reproductive potential is sustained for decades. In females, reproduction is more cyclical, shaped by the monthly rhythm of the ovarian and menstrual cycles. Follicle-stimulating hormone stimulates the development of follicles within the ovaries, each containing an immature egg. As the follicles grow, they secrete estrogen, which prepares the uterine lining for potential implantation. Around the midpoint of the cycle, a surge of luteinizing hormone triggers ovulation, releasing the mature egg. The ruptured follicle transforms into the corpus luteum, which secretes progesterone to stabilize the uterine lining. If fertilization does not occur, the corpus luteum degenerates, hormone levels fall, and the uterine lining is shed in menstruation. This cycle repeats, month by month, guided by the precise interplay of hormones from the hypothalamus, pituitary, and ovaries. The complexity of this cycle reflects more than just reproduction. It influences mood, energy, and well-being, demonstrating how hormones ripple outward beyond their immediate purpose. Estrogen supports bone and cardiovascular health, progesterone calms the nervous system, and the fluctuations of both contribute to emotional states. The reproductive cycle is thus not confined to fertility, but extends into the broader landscape of health and daily life. When fertilization occurs, hormones again take on extraordinary roles. The early embryo begins producing human chorionic gonadotropin, which sustains the corpus luteum and its secretion of progesterone. Progesterone prevents menstruation and maintains the uterine lining, creating a safe environment for the developing embryo. As pregnancy advances, the placenta becomes the primary endocrine organ, producing hormones such as estrogen, progesterone, and human placental lactogen. These hormones adapt the mother's physiology to support the growing fetus, increasing blood supply, altering metabolism, and preparing the breasts for milk production. The placenta thus joins the endocrine system as a temporary but vital gland, ensuring that both mother and child are sustained. Childbirth itself is triggered and guided by hormones. Toward the end of pregnancy, rising estrogen levels increase the sensitivity of the uterus to oxytocin. Oxytocin, released in pulses from the posterior pituitary, stimulates uterine contractions, while prostaglandins reinforce this process. Together, they initiate labor, moving the fetus into the birth canal, and eventually into the world. After delivery, oxytocin continues to act, contracting the uterus to prevent bleeding and promoting the letdown reflex that allows milk to flow during breastfeeding. These events highlight the dual role of oxytocin as both a physical and emotional hormone, fostering not only contractions and milk release but also the bonding between mother and child. Prolactin, secreted by the anterior pituitary, is another key hormone in reproduction, particularly in the nurturing stage after birth. It stimulates the production of milk in the mammary glands, ensuring that the newborn has nourishment. Prolactin levels rise during pregnancy, but are kept in check by high estrogen and progesterone. After birth, when these hormones decline, prolactin takes full effect, initiating lactation. Nursing itself further stimulates prolactin release, creating a cycle in which the act of feeding sustains the ability to feed. Prolactin also influences behavior, often fostering calmness and attentiveness, qualities that support caregiving. Hormones not only guide reproduction in individuals, but also adapt to life stages and transitions. In women, menopause marks the end of reproductive capacity, as the ovaries cease producing eggs and hormone levels decline. Estrogen and progesterone fall, leading to changes in cycles, mood, bone health, and cardiovascular function. In men, testosterone levels decline more gradually, sometimes leading to changes in fertility, energy, and body composition. These transitions reflect the natural course of life, showing that hormones shape not only beginnings but endings, guiding the body through its full arc. Disorders of reproductive hormones illustrate their importance. In women, conditions such as polycystic ovary syndrome disrupt normal hormone balance, leading to irregular cycles, infertility, and metabolic challenges. In men, low testosterone can impair sperm production, reduce vitality, and affect mood. Infertility, whether male or female in origin, often reflects disruptions in the hypothalamic pituitary gonadal axis. Treatments often involve adjusting hormones, whether through stimulation of ovulation, replacement of deficient hormones, or regulation of excess. These approaches demonstrate how deeply reproduction depends on the orchestration of endocrine signals. Yet reproduction is not only about fertility and pregnancy. Hormones also shape the emotional and social dimensions of human life. Oxytocin, dopamine, and sex hormones influence attraction, bonding, and intimacy, weaving biology into the fabric of relationships. The pleasure of touch, the bond between partners, and the attachment between parent and child are all reinforced by hormones, showing that reproduction is not simply mechanical, but deeply connected to the experiences of love and connection. Reflecting on hormones and reproduction in depth reveals the extraordinary scope of the endocrine system. From the awakening of puberty to the cycles of fertility, from the adaptations of pregnancy to the nurturing of new life, from the transitions of menopause and aging to the emotional bonds that sustain families, hormones guide every stage. They ensure not only the continuation of species but also the richness of human relationships. In their rhythms, rises, and falls, they carry forward the story of life, generation by generation, linking past to future in the quiet language of chemistry. 17. Hormones and aging. Aging is a universal journey, a gradual unfolding of time within the body that brings changes in strength, appearance, and resilience. Though it is often thought of in terms of years or visible features, aging is also a hormonal story. The endocrine system, which so carefully balances growth, reproduction, metabolism, and mood during earlier life, gradually shifts its patterns as the decades pass. Hormones decline, rhythms alter, and the signals that once directed vigorous activity give way to slower, quieter processes. To understand aging through the lens of hormones is to see how the body adapts to time, adjusting its chemistry to meet new needs and to conserve energy for the later chapters of life. One of the most significant hormonal changes of aging occurs in the reproductive system. In women, the transition of menopause marks the end of ovarian activity. Estrogen and progesterone, once secreted in monthly rhythms, decline sharply as the ovaries cease releasing eggs. This change brings an end to fertility, but also affects many other aspects of health. The absence of estrogen reduces bone density, contributing to osteoporosis in later years. It influences the cardiovascular system, increasing the risk of heart disease, and it alters fat distribution, often leading to a shift from hip and thigh storage to abdominal storage. Menopause is also associated with changes in mood, sleep, and skin, all reflecting the wide influence of estrogen throughout the body. Hot flashes, night sweats, and fluctuations in energy are outward signs of the body adjusting to this new hormonal landscape. In men, the decline of reproductive hormones is more gradual. Testosterone levels peak in early adulthood and then slowly decrease over time. This decline, sometimes called andropause, is less abrupt than menopause, but still significant. Lower testosterone levels can lead to reduced muscle mass, decreased energy, lower libido, and subtle changes in mood. Like estrogen, testosterone supports bone strength, and its decline contributes to skeletal fragility. The changes are less sudden than in women, but equally tied to the story of aging, showing how the body's chemistry gradually adjusts its emphasis from reproduction to maintenance. Other endocrine glands also undergo age-related changes. The pituitary gland, once the master conductor of growth and development, shifts its emphasis as demands change. Growth hormone secretion, which peaks during adolescence and supports tissue repair in adulthood, declines steadily with age. This reduction is sometimes called somatopause and contributes to the changes often associated with aging: reduced muscle mass, increased fat, slower healing, and diminished vitality. While the decline is natural, it highlights how growth hormone is not only for the young but remains important throughout life for maintenance and repair. The thyroid gland, too, may alter with age. Though not all individuals experience major changes, some show reduced thyroid activity, leading to lower metabolism, fatigue, and weight gain. Even subtle shifts in thyroid hormones can influence mood and energy, revealing how sensitive the body is to their regulation. In some cases, autoimmune conditions affecting the thyroid become more common with age, further illustrating the interplay between the endocrine system and the immune system across the lifespan. The adrenal glands, producers of cortisol, continue their role in stress adaptation, but their rhythms may shift with age. Some older individuals experience higher evening cortisol levels, which can disrupt sleep and contribute to fatigue. Prolonged cortisol exposure can also accelerate muscle breakdown and impair memory, linking hormonal changes to the cognitive and physical declines often seen in aging. Yet the adrenal glands also provide resilience, ensuring that even as other hormones wane, the body retains the capacity to respond to challenge and change. The pineal gland, with its secretion of melatonin, plays an important role in aging as well. Melatonin levels often decline with age, reducing the strength of circadian rhythms. This may explain why older adults frequently experience disrupted sleep, lighter rest, or earlier waking. Since melatonin also has antioxidant properties, its decline may contribute to cellular aging more broadly. Restoring healthy rhythms through light exposure, regular routines, and sometimes supplementation illustrates the importance of this small gland even in later life. Insulin regulation also shifts with aging. Cells may become less sensitive to insulin, leading to higher blood sugar levels and an increased risk of type 2 diabetes. This condition reflects the gradual decline of metabolic efficiency, as tissues respond less effectively to hormonal signals. Combined with reduced physical activity and changes in body composition, insulin resistance becomes a significant feature of aging metabolism. It highlights again how the balance between hormones and tissues must be carefully maintained, and how subtle shifts can influence overall health. The decline of hormones with age has sparked interest in replacement therapies, from estrogen and progesterone for postmenopausal women to testosterone for aging men and growth hormone for older adults. While such therapies can alleviate some symptoms and restore certain functions, they also carry risks, reflecting the delicate balance of the endocrine system. Too much replacement can disrupt natural feedback loops, create imbalances, or increase risks of disease. The lesson of aging may be less about holding on to youthful hormone levels and more about adapting gracefully to the natural transitions, supporting the body in its new balance rather than forcing it into an old one. Hormones and aging are not only about physical changes but also about the deeper experience of life. The decline of reproductive hormones shifts the focus from fertility and growth to stability and reflection. The reduction of growth hormone and melatonin emphasizes conservation rather than expansion, allowing the body to rest more than build. Even cortisol, with its altered rhythms, reflects the way stress responses evolve with time. The body is not failing but adapting, finding new ways to sustain itself in later years. Yet even in decline, hormones continue to sustain vitality. Estrogen and testosterone do not vanish entirely but persist at lower levels, supporting health in quieter ways. Growth hormone still pulses during sleep, even if less dramatically. Cortisol still rises to meet challenges, and melatonin still signals the night. The endocrine system continues to guide the rhythms of life, not with the intensity of youth but with the endurance of age. Reflecting on hormones and aging invites us to see time not as an enemy but as a companion. The changes of aging are not failures of the body but transitions into new stages, guided by shifts in chemistry that reflect changing priorities. Where once the emphasis was on growth and reproduction, later life emphasizes repair, adaptation, and resilience. Hormones are the silent guides of this transition, ensuring that the body remains balanced even as its needs change. In the grand story of the endocrine system, aging is the final chapter, but it is not a chapter of decline alone. It is one of adaptation, of shifting rhythms, of the body finding new balance with time. Hormones write this story in quiet pulses, reminding us that life is not about resisting change, but about moving with it, carrying forward strength in new forms. The endocrine system, from birth to old age, ensures that we are not static but always adapting, always guided by the quiet currents of its chemical messengers. 18. Endocrine disorders and imbalances. The endocrine system, with its quiet messengers drifting through the bloodstream, usually maintains a remarkable state of balance. Hormones rise and fall with precision, ensuring that growth, metabolism, reproduction, mood. Yet this balance is delicate, and when it is disrupted, the effects ripple outward into every aspect of life. Endocrine disorders and imbalances reveal just how deeply hormones shape human health. They show us what happens when glands falter, when receptors fail to respond, or when feedback loops are disrupted. While each disorder has its own story, they all illustrate the importance of harmony in the body's chemical symphony. One of the most well-known endocrine disorders is diabetes mellitus, a condition in which the regulation of blood glucose is impaired. In type 1 diabetes, the immune system mistakenly destroys the insulin-producing beta cells of the pancreas, leaving the body without the means to lower blood sugar. Without insulin, glucose remains in the bloodstream, while cells starve for energy. Treatment requires lifelong insulin replacement, a reminder that a single hormone can mean the difference between survival and decline. Type 2 diabetes, more common, develops when the body's cells become resistant to insulin. The pancreas initially compensates by producing more, but over time, this too falters. The result is elevated blood sugar, increased fat storage, and long-term complications affecting blood vessels, kidneys, nerves, and eyes. Both forms of diabetes underscore the importance of insulin as a regulator of metabolism and the vulnerability of this balance to disruption. Thyroid disorders are another major category of endocrine imbalance. In hypothyroidism, the thyroid gland produces too little hormone, slowing metabolism, fatigue, weight gain, cold intolerance, dry skin, and slowed thinking. become evident. If untreated, the condition can progress to myxedema, a severe state of metabolic decline. In hyperthyroidism, by contrast, the thyroid produces too much hormone, speeding metabolism to an unhealthy pace. Weight loss, rapid heartbeat, nervousness, and heat intolerance characterize this condition. Graves' disease, an autoimmune disorder, is one of the most common causes. Both hypo and hyperthyroidism reveal how thyroid hormones, though small in structure, have vast effects on nearly every tissue of the body. The adrenal glands are also susceptible to disorders. Addison's disease, caused by insufficient production of cortisol and often aldosterone, leads to fatigue, low blood pressure, weight loss, and darkening of the skin. In times of stress, individuals with Addison's disease may experience adrenal crisis, a life-threatening condition without prompt treatment. On the opposite end, Cushing's syndrome arises when cortisol levels are chronically elevated, often due to a pituitary tumor producing excess adrenocorticotropic hormone, or from prolonged use of corticosteroid medications. Symptoms include weight gain, thinning skin, muscle weakness, and impaired immunity. These disorders highlight the importance of cortisol in stress adaptation and the dangers of both too little and too much. Disorders of growth hormone provide another perspective. In children, deficiency results in short stature and delayed development, while excess causes gigantism, with extreme height and enlarged features. In adults, deficiency may lead to fatigue, increased fat, and fragile bones, while excess produces acromegaly, in which hands, feet, and facial features thicken, sometimes accompanied by organ enlargement. Because growth hormone influences not only height but also metabolism and tissue repair, its imbalance affects both structure and function throughout life. The parathyroid glands, small as they are, can cause significant problems when their function falters. Overactivity of these glands leads to hyperparathyroidism, in which excess parathyroid hormone elevates blood calcium levels. Bones weaken as calcium is drawn out. Kidney stones may form, and muscles and nerves function abnormally. Underactivity, or hypoparathyroidism, produces the opposite problem, with low calcium levels leading to muscle spasms, tingling, and in severe cases, seizures. These conditions remind us that even the smallest endocrine glands have vast importance, and their imbalances quickly disrupt the stability of life. Reproductive hormone imbalances affect both men and women in profound ways. In women, polycystic ovary syndrome is one of the most common endocrine disorders, characterized by elevated androgens, irregular menstrual cycles, and often insulin resistance. It affects fertility and metabolism alike, demonstrating the interconnectedness of endocrine pathways. In men, low testosterone may result from testicular failure or pituitary dysfunction, leading to reduced libido, fatigue, and muscle loss. Imbalances in estrogen and progesterone also underlie conditions such as endometriosis, infertility, and menopausal symptoms, showing how reproductive hormones influence not only fertility, but overall health and well-being. Pituitary tumors, though often benign, can disrupt hormone production dramatically. Depending on the cells involved, they may cause overproduction of prolactin, growth hormone, or adrenocorticotropic hormone. Prolactinomas, for instance, can lead to infertility, menstrual disturbances, and milk secretion outside of pregnancy. Excess growth hormone leads to acromegaly, while excess ACTH drives Cushing's disease. Conversely, pituitary tumors can also impair normal hormone secretion, leading to deficiencies in multiple systems. Because the pituitary is the master gland, its imbalances ripple outward to thyroid, adrenal, gonadal, and growth processes, illustrating the central role it plays. Even the pineal gland, though small, can experience disruptions that affect sleep. Reduced melatonin production, whether from aging or excessive artificial light exposure, can lead to insomnia or disrupted circadian rhythms. Seasonal affective disorder, influenced by changes in light and melatonin cycles, demonstrates how sensitive mood and sleep are to endocrine timing. Though less life-threatening than other endocrine disorders, these imbalances highlight the importance of rhythm in human well-being. Obesity is another condition deeply influenced by endocrine signals. Hormones such as leptin, ghrelin, and insulin interact to regulate appetite and energy balance. In obesity, leptin levels are often high, but the brain becomes resistant to its signals, a condition known as leptin resistance. The result is persistent hunger despite adequate energy stores. Ghrelin, the hunger hormone, may also be elevated, further fueling appetite. These imbalances reveal that body weight is not simply a matter of willpower, but is profoundly shaped by endocrine regulation. Some endocrine disorders are rare but striking. Pheochromocytoma, a tumor of the adrenal medulla, produces excess adrenaline and noradrenaline, leading to episodic surges of blood pressure, rapid heartbeat, sweating, and anxiety. Though uncommon, it illustrates the powerful effects of catecholamines when unregulated. Another rare condition, congenital adrenal hyperplasia, involves enzyme defects in cortisol production, leading to excess androgen production and disrupted development. These cases demonstrate how delicate the pathways of hormone synthesis are, and how a single missing enzyme can alter life profoundly. Despite the challenges they bring, endocrine disorders also teach us resilience. Treatments often involve restoring balance, whether through hormone replacement, surgical removal of tumors, or medications that block excess secretion. Insulin therapy for diabetes, thyroid hormone for hypothyroidism, cortisol for adrenal insufficiency, and growth hormone for deficiency all demonstrate how modern medicine can step into the body's natural rhythms and support them when they falter. These therapies, though artificial in origin, are often nearly identical to the body's own hormones, highlighting the precision of endocrine knowledge. Reflecting on endocrine disorders and imbalances reminds us of the extraordinary complexity of the body's chemical communication. The system works so seamlessly most of the time that we are unaware of it. But when it falters, the importance of harmony becomes clear. Whether through too little hormone, too much, or disrupted sensitivity, the balance is delicate. Yet the body's capacity for adaptation, supported by medicine and care, often allows restoration. In the story of the endocrine system, disorders are not simply failures but opportunities to see more clearly the importance of balance. They reveal how each gland contributes to the whole, how each hormone plays multiple roles, and how interconnected the body truly is. They remind us that life is not only about perfection but about resilience, about the capacity to restore equilibrium after disruption. Through the study of these imbalances, we come to appreciate even more the silent harmony that sustains health each day. 19. Integration of the nervous and endocrine systems. The body does not operate as a collection of separate parts but as a unified whole. And nowhere is this clearer than in the partnership between the nervous and endocrine systems. These two great regulatory networks, one electrical and the other chemical, work together to maintain balance, guide responses, and shape the experience of life. The nervous system, with its swift impulses carried along neurons, provides immediacy, while the endocrine system, with its hormones drifting through the bloodstream, offers endurance. Together, they form a dynamic duo that ensures the body can both react instantly and sustain long-term adaptation. To understand their integration is to see how thought, emotion, movement, and physiology are woven into a seamless whole. At the center of this partnership lies the hypothalamus, a small region of the brain that acts as a bridge between neural signals and hormonal responses. The hypothalamus receives input from across the nervous system, signals about light from the eyes, about internal states from the body, and about emotions from higher brain centers. In response, it releases hormones that act directly on the pituitary gland, which then influences nearly every endocrine organ. Through this pathway, the nervous system communicates its needs to the endocrine system, ensuring that the body's chemistry adjusts in harmony with its perceptions. If the brain perceives danger, the hypothalamus initiates the stress response. If it perceives nightfall, it signals for melatonin release. The hypothalamus is therefore both a processor of information and a master regulator of hormones. One of the most striking examples of integration is the stress response. When the nervous system perceives a threat, the sympathetic branch activates instantly, sending impulses to the adrenal medulla. Within moments, adrenaline and noradrenaline are released, spreading through the blood to increase heart rate, dilate airways, and prepare the body for action. At the same time, the hypothalamus activates the hypothalamic pituitary adrenal axis, leading to the release of cortisol. This slower hormonal response sustains the body's readiness, mobilizing energy for minutes or hours after the initial alarm. Here we see the nervous system and the endocrine system working hand in hand, one providing the immediate spark, the other the steady flame. Reproduction offers another example of this partnership. Sexual arousal begins with sensory input processed by the nervous system, but hormones guide fertility, ovulation, and long-term reproductive cycles. The hypothalamus releases gonadotropin-releasing hormone impulses, prompting the pituitary to release luteinizing hormone and follicle-stimulating hormone, which act on the ovaries and testes. The nervous system initiates behavior and sensation, while the endocrine system sustains the background conditions of fertility. In childbirth, oxytocin exemplifies this integration further. It is released in response to neural signals from the stretching uterus, yet it acts hormonally to stimulate more contractions, creating a positive feedback loop that blends nerve impulses and hormonal release seamlessly. Even something as simple as eating illustrates the integration of these systems. The sight and smell of food, processed by the nervous system, can trigger insulin release from the pancreas before any nutrients enter the blood. This anticipatory response ensures that glucose can be absorbed efficiently once digestion begins. Meanwhile, hormones like ghrelin and leptin inform the brain of hunger and satiety, creating a dialogue between body and mind. The nervous system perceives the world and initiates actions, while hormones provide longer-term adjustments, ensuring that energy is balanced across hours and days. The regulation of daily rhythms provides another perspective on integration. Light entering the eyes activates neural pathways to the suprachiasmatic nucleus, the brain's master clock. This neural signal is then translated into hormonal language by the pineal gland, which secretes melatonin in response to darkness. The nervous system perceives the environment, while the endocrine system translates that perception into physiological rhythms. Together, they align sleep, metabolism, and energy with the cycles of day and night. Without this partnership, the body would lose its synchrony with the world around it. The immune system also reflects the integration of nervous and endocrine control. Stressful thoughts, perceived by the brain, can trigger hormonal cascades that suppress or stimulate immunity. Cortisol, released in response to prolonged stress, reduces inflammation, protecting the body from overreaction. Oxytocin and prolactin, by contrast, can enhance aspects of immune function, showing that the chemistry of care and bonding extends even into defenses. The nervous system's perceptions influence the endocrine system's outputs, which in turn shape immunity and health. The feedback between these systems is continuous and multidirectional. Hormones influence the nervous system just as much as the nervous system influences hormones. Cortisol alters mood and memory, Estrogen modulates the sensitivity of serotonin pathways. Thyroid hormones affect alertness and cognition. Even small hormonal shifts can change how the brain processes the world, while neural experiences, stress, joy, anticipation, can change hormonal flows. This constant interplay ensures that body and mind are not separate realms but two aspects of a single process. Life stages reveal how this integration evolves. In infancy, the nervous and endocrine systems work together to establish basic rhythms of sleep, feeding, and growth. In adolescence, the surge of sex hormones interacts with neural circuits to create the intensity of teenage emotion and drive. In adulthood, stress responses balance the demands of life, while in aging, shifts in both systems alter sleep, mood, and resilience. At each stage, the nervous and endocrine systems adapt together, guiding the transitions of life as a coordinated pair. Disorders further highlight this integration. A tumor in the pituitary, though endocrine in nature, can cause neurological symptoms by pressing on nearby nerves. Conversely, traumatic brain injury can disrupt hormonal regulation by damaging the hypothalamus or pituitary. Depression, anxiety, and cognitive disorders often involve hormonal components, while endocrine disorders such as hypothyroidism or Cushing's syndrome can produce profound psychological effects. These conditions remind us that nervous and endocrine health cannot be separated. They are threads of the same fabric. Even emotions themselves are examples of this integration. Fear begins as a perception in the nervous system, but is sustained by adrenaline and cortisol. Love involves dopamine and oxytocin interacting with neural reward circuits. Calmness reflects parasympathetic neural activity, supported by serotonin and melatonin. Emotions are not solely in the mind nor solely in the body. They are woven from the integration of nerves and hormones. This perspective reveals the unity of human experience, where thought, feeling, and physiology are inseparable. Reflecting on the integration of the nervous and endocrine systems reveals the wisdom of dual design. Electricity and chemistry, nerves and hormones, work together to ensure that life is both swift and enduring. A sudden shock can trigger instant neural responses, while long-term adaptation is carried by hormonal flows. The two systems complement one another, filling in each other's limitations and amplifying each other's strengths. Without nerves, the body would be too slow to react. Without hormones, it would be too fragile to sustain. Together, they form the foundation of adaptation, resilience, and continuity. In the grand symphony of life, the nervous system provides the quick notes, sharp and immediate, while the endocrine system provides the long tones, slow and sustaining. It is the harmony between them that creates coherence. Their integration ensures that the body is not a machine of disconnected parts, but a living whole, responding to the world with unity and grace. This partnership carries us through every moment, from the racing heart of fear to the steady calm of sleep, reminding us that life is always a dialogue between the fast and the slow, the fleeting and the enduring. 20. A gentle conclusion. As we come to the end of this long journey through the endocrine system, it is worth pausing to reflect on the remarkable world we have explored. From the smallest of glands hidden deep in the brain to the larger organs that rest within the chest and abdomen, each has revealed itself as a quiet participant in the story of life. Their messages, carried invisibly through the bloodstream, form a language of balance, one that sustains the body from its earliest moments in the womb to its final breaths in old age. These chemical messengers, hormones, are never loud, never forceful, yet their influence extends into every corner of human experience. They shape growth, metabolism, reproduction, mood, stress, and aging, ensuring that the body is not a collection of separate parts, but a coordinated whole. At the beginning of life, hormones direct development, guiding tissues and organs into place and preparing the body for birth. Growth hormone and thyroid hormones sculpt the skeleton. Insulin ensures energy supply, and cortisol helps the infant breathe at the moment of arrival. From the very start, the endocrine system ensures that life is possible. Childhood then unfolds under its gentle supervision, with growth hormone lengthening bones, the thyroid maintaining metabolism, and the pancreas balancing glucose. These processes happen quietly, unnoticed, yet they allow the child to play, learn, and flourish. Adolescence brings a more dramatic transformation, when reproductive hormones awaken and reshape the body into its adult form. Testosterone deepens the voice and strengthens muscle. Estrogen softens features and prepares for fertility, while progesterone establishes cycles of reproduction. These changes are not only physical but emotional, with mood, motivation, and identity all shaped by hormonal surges. It is during this stage that the endocrine system reveals its role not just in survival, but in the richness of human experience, touching aspects of life that extend beyond biology into love, connection, and the sense of self. Adulthood is a time of balance, when hormones maintain steady rhythms that allow for stability. The pancreas continues its quiet regulation of glucose. The thyroid sustains metabolism. The adrenal glands respond to stress, and the gonads maintain fertility. Each gland contributes to the harmony, allowing individuals to work, create, nurture, and explore. It is in adulthood that the importance of hormonal balance becomes most evident, for imbalances can disrupt not only physical health, but also emotional well-being, energy, and resilience. Yet even here, the endocrine system usually maintains its subtle equilibrium, adapting to the challenges of daily life without conscious effort. As years advance, hormones begin to shift again. Growth hormone declines, melatonin lessens, and reproductive hormones ebb. Menopause brings an end to cycles of fertility, while testosterone decreases gradually in men. These changes alter metabolism, mood, and energy, but they also reflect a new stage of life, one that emphasizes reflection and adaptation rather than growth and reproduction. Aging is not a failure but a transition, and hormones guide this transition with the same quiet care that has marked every stage before. They allow the body to adapt to time, conserving resources and preparing for rest. Along the way, we have seen how hormones not only regulate the body, but also shape the inner landscape of mood and thought. Oxytocin fosters bonding and trust. Cortisol sharpens alertness and stress. Melatonin invites sleep, and dopamine encourages motivation. These influences remind us that emotions are not separate from the body but part of its dialogue, woven from the same chemistry that sustains heartbeat and breath. The endocrine system is thus both physical and experiential, both structural and emotional, guiding the whole person in ways that often escape awareness yet are deeply felt. Disorders and imbalances, though challenging, have shown us the importance of harmony. Diabetes illustrates the consequences of insulin deficiency or resistance. Thyroid disease shows how metabolism falters when the gland is over or underactive, and adrenal disorders reveal the dangers of cortisol excess or deficiency. Yet treatments, often in the form of replacement hormones, demonstrate how closely medicine can align with nature's design, restoring balance where it has been lost. These conditions, while burdensome, remind us of the resilience of the body and the precision of its regulation. Perhaps most striking of all is the integration between the endocrine and nervous systems. Together, they form the great regulatory duet of life, with the nervous system providing speed and precision, and the endocrine system offering endurance and depth. The hypothalamus stands at the crossroads, translating neural signals into hormonal commands, ensuring that the body's chemistry reflects both the outer environment and the inner state of mind. This integration shows that life is not fragmented but whole, that thought and feeling are inseparable from physiology, and that every response is both neural and hormonal at once. Throughout this exploration, a theme emerges: the importance of rhythm. Hormones rise and fall with daily cycles, responding to light and darkness, wakefulness and sleep. They fluctuate with monthly cycles, guiding fertility and reproduction. They shift with seasonal rhythms, responding to the changing environment. They alter across the decades, marking the stages of childhood, adolescence, adulthood, and aging. These rhythms reveal that life is not static but dynamic, always in motion, always adjusting. The endocrine system is the timekeeper of the body, ensuring that these rhythms remain in harmony with the world. To reflect on the endocrine system is to reflect on balance. Too much or too little of any hormone can disrupt the body, but when levels are just right, health is sustained without our awareness. It is a system that does its work silently, without applause. Yet without it, nothing else could function. The beating of the heart, the clarity of thought, the cycles of fertility, the endurance of stress, and the renewal of sleep all depend on the steady, invisible flow of hormones. In the quiet of night, when melatonin rises and growth hormone pulses, the body repairs itself and prepares for the day ahead. In the light of morning, cortisol lifts alertness, and insulin prepares the body to receive energy from food. At times of challenge, adrenaline and cortisol mobilize strength. At times of intimacy, oxytocin deepens bonds. In every moment, hormones shape the unseen currents of life. They are the silent guardians of health, the hidden architects of growth, the unseen conductors of balance. In closing, the story of hormones and the endocrine system is the story of life itself, a story of growth, adaptation, reproduction, resilience, and renewal. It is a story written not in words but in molecules, carried in the bloodstream, whispered from gland to tissue. It is a story that begins before birth and ends only at life's conclusion, guiding each moment in between. To listen to this story is to gain a deeper appreciation of the body's quiet wisdom, the harmony it maintains, and the rhythms it follows. The endocrine system is a reminder that strength does not always shout, that guidance can be silent, and that balance is often maintained in ways too subtle to notice. In its whispers, it sustains us. In its rhythms, it carries us. In its constancy, it reminds us that life is a harmony of the seen and the unseen. And as the body rests, lulled by its own chemistry into sleep, the endocrine system continues its quiet work, ensuring that tomorrow arrives with strength, balance, and renewal.